Yes, it is. It is there. You can
Okay,
proceed.
shall I start? Shall I start?
Yes, you can start.
Okay. Greetings to everybody, and I'm very grateful for the opportunity to talk at this conference. Unfortunately, not so many of us, but maybe it makes the discussion more productive, I would say. So don't hesitate to interrupt me if you have any questions, because the audience is small and we should not be stick to formal procedure. I will tell you something about, let me introduce myself briefly. My name is Michael Tibelsky, and my affiliation, this is my university. This is the oldest one in Russia and the largest one. So it has more than 250 years old history. And maybe that's enough for brief introduction. So outline. I will tell you something about the historical grounds, then the physical grounds. Then we discussed light scattering by small particles, the well-known Rayleigh scattering and Rayleigh approximation. Then I will show that there are a window in the parameter range where the Rayleigh approximation is completely erroneous and doesn't work at all. And new type of scattering, which we name anomalous scattering, arises. And we will see that this anomalous scattering has practically nothing in common with what we used to know about the scattering by small particles. And then we discuss high index dielectric particles and peculiarities of scattering by these particles. Specifically, we will discuss tunable scattering diagrams, giant field concentration, so-called funnel effect. Then we jump to dynamic scattering, and finally to conclusion, main publications and funding. So light scattering by a sphere. This is a very old problem, and the exact solution exists since Lorentz produced it in 1890, so many years ago. And from the mathematical point of view, the problem is completely solved. But this is not the case from the physical point of view, because the solution is very cumbersome. It depends on problem parameters, and this dependence is very complicated. And new domains, different domains of the problem parameters correspond to completely different physical properties of the scattering particles. And this part of the problem is not completed yet. The new range of parameters correspond to new scattering peculiarities, and that is the point we will focus on. Why it is so important nowadays? Basically because of huge demand from nanotechnologies. And the main questions are how to overcome the diffraction limit, how to manipulate with light at the scale much smaller than the wavelengths, and how to tailor and control the radiation pattern at a sub-wavelength scale. These questions are important both from academic points of view and from the point of view of numerous applications. And of course, there is a coupling between these two branches of interest, and both enhance each other. So light scattering by small particles. Everybody knows this simple and very well-known expression for the dipole scattering, cross-section of the dipole scattering, which describes the scattering by small particles. And specifically, the blue color of sky we are enjoying with is related to this expression. And there are beautiful sunsets and sunrises also. Epsilon here is the permittivity of the scattering particle. X is a dimensionless quantity which is called size parameter. Actually, this is the dimensionless size of the particle. Now look at the denominator of this expression. We have two quantities, and when epsilon equals -2, the denominator vanishes. And it means that the cross-section diverges. Of course, epsilon is a complex quantity, and there is an imaginary part related to dissipation, and it remains in the denominator, so it is not the exact zero, but nonetheless, it doesn't help much because there are no fundamental restrictions for the value of the imaginary part. And if the imaginary part is very small, we will see that a particle with the size of a few nanometers has a cross-section of several square kilometers, which of course is nonsense. What is wrong in this reasoning? We have forgotten that the particle is a cavity and it has its own eigenmodes. And when the frequency of the incident wave coincides with that for the eigenmodes, we have resonances. And at small dissipation, we have very sharp resonances. And these resonances correspond to oscillations of the charged particles, electrons, either because epsilon is negative, it's usually is metal, and metals have free electrons. So usually these oscillations are related to the free electron gas. And the oscillations of charged particles gives rise to an emission of electromagnetic radiation or to losses of energy, even if we do not have any dissipation at all. This is also a well-known effect. It's called radiative losses, and the corresponding excitations, eigenmodes, are known as surface plasmons. And these radiation losses usually are very weak and can be neglected. But if we have very weak dissipation, this effect becomes dominant. And then we have some additional term at the imaginary part of the permittivity related to this process, which I name gamma radiative. And if epsilon is small, the gamma radiative and epsilon prime equals -2, we have just gamma radiative in the denominator. It's a small quantity, but a finite quantity. And this quantity, in contrast to the imaginary part of the permittivity, which is a constant at a given frequency, gamma radiative depends on the problem parameter, on the size parameter. And this dependence is very sharp. As a result of the dependence on the cross-section of the problem parameter becomes very unusual. In particular, we used to know that usually the dipole scattering is the dominant for a small particle. Here we have the cross-section, quadrupole cross-section, which is larger than the dipole cross-section, octupole cross-section larger than the quadrupole cross-section, and so on. So we have what we call inverted hierarchy of resonances. And there are many other peculiarities which I don't have time to discuss now. Then I will focus just on a few aspects of this scattering, which I called anomalous scattering. That is what I said already. And the conclusion is that the Rayleigh approximation may be, and at small enough dissipation rate always is, erroneous, regardless smallness of the particle. So how to calculate these radiative losses, gamma radiative? Fortunately, it is already done because, as I said, we have the exact solution. And the only thing we have to do is to extract from this exact solution the quantity which we're looking for. So then we have to replace the Rayleigh approximation by the exact solution and to manipulate it. It has been done, and the results are presented here. As I said, I will focus just on the radiative pattern. You can see the particle, which is substantially sub-wavelengths, so the ratio of the radius to the wavelengths is very small. Nonetheless, we have a very complicated pattern of the Poynting vector field. The radiation in this case goes from the bottom to the top of the picture, and this blue circle is the surface of the sphere. The color corresponds to the intensity, and the streamlines are shown as white lines. We can see a number of singular points. We will gradually approach the exact value of the dipole resonance for these parameters, and you will see how drastically the pattern will change. A number of singular points will bond, move, merge, and annihilate. What is important in this picture is, this is the center of localized plasmon that I said, and what is important is what we call funnel. There are separatrix which collect the radiation from a large area downstream and convey this radiation to the immediate vicinity of the particle, making in this area a huge concentration of the electromagnetic power. That is why we have so high intensity of the electromagnetic field in the substantially sub-wavelength scale. This is important. So I will show you briefly these patterns. So I will focus just on optical vortices, which appears here spontaneously. We don't have to produce, we don't need to produce special equipment for making these optical vortices. They are coming into being spontaneously just because of the properties of the scattering problem. And so on and so forth. In 3D, it's even more complicated. You could see some streamlines in three-dimensional space related to one of the previous two-dimensional pictures, which correspond to the equatorial cross-section of the pattern. And again, you could see the center of localized plasmons. Then you could see the energy which stream in, which comes from downstream and is transported to the optical vortices. And then after a number of circulation around the singular point, the energy goes to infinity. So this is a stream out. To give you an impression about the structure of this field, I show just two streamlines. The color corresponds to the intensity normalized over the intensity of the incident wave. And you can see that we can achieve the enhancement of the intensity about 300 times. And the structure is very complicated. And this is the scale. This is the wavelengths of the incident wave. So you could see that the entire complicated pattern has a very small size relative to the wavelengths of the radiation. And it depends drastically, as you could see from the previous slides, from the frequency, on the frequency of the incident wave. And it gives rise to the opportunity to control the pattern at the sub-wavelength scale, which is one of the most important demands from applications. So, okay, all this is very good and interesting, but the question is why it is not used so widely in various applications. The problem is that metal particles do not exhibit pronounced resonances because of dissipation. We have seen that the small dissipation, weak dissipation, is a very important feature of the phenomena to be observable. But unfortunately, all metals except these three are characterized with large dissipation at optical frequency. And these three metals, aluminum, potassium, and sodium, are chemically active, and they are not convenient for practical purposes. Can we replace metals with dielectrics? Yes, we can. The dielectrics do not have plasmon modes because epsilon is positive, but instead we have oscillation of polarization, polaritonic modes. And then instead of the oscillation of free electron gas, we have oscillation of bound charges and displacement current instead of conduction current. We also consider particles with larger effective index, and it will be seen shortly why we need them. So advantages of this consideration is that there are plenty of materials with low dissipative losses at resonances, and disadvantage is that the particles should be relatively large, so that the resonance condition should be fulfilled. Then, because we have the refractive index in the denominator here, if the refractive index is large, then simultaneously we can fulfill the resonance condition and the geometric smallness of the particle. So that's what we need. And these two conditions could be held simultaneously. So materials, which materials are useful for this purpose? Fortunately, again, there are plenty of these materials which are produced in industrial scales. These materials are just usual semiconductors. You could see that at optical frequency, we have large real part of the refractive index and practically zero imaginary part, practically zero dissipation. So then what happens with these materials? As I said, in this solution, it is convenient to introduce the dimensionless scattering efficiency to normalizing the scattering cross-section on the geometrical cross-section. And then in this solution, the total efficiency is presented as an infinite series of multipolar partial efficiencies. And each of them are related to the so-called electric and magnetic amplitudes, which in turn depends in a complicated way on the problem parameters. So here I show these partial efficiencies calculated based on the exact solution for epsilon equals this value. You could see mass of different lines with very strong overlap. What happens if epsilon is large? If epsilon is large, then we have large polarizability, then we have large resonant amplitude, then we have large quality factor, and then we have narrow resonance line. Finally, it results in big overlap, and altogether provides us with the opportunity of a selective excitation of resonant modes and to tailor the interference. This is a similar picture, but the real part of the epsilon is increased 10 times. You can see nothing similar to the left plot. We have well-pronounced separated resonance lines related to excitation of different multipoles, and then we have a very interesting radiative pattern. So this is in 3 dimensions, and you could see that X is, I remind you, this size parameter. Actually, this is either the dimensionless radius or dimensionless frequency. And then just weak variation of the size of the particle or weak variation of the frequency of the incident light gives us the opportunity to tailor any scattering diagram, whatever we want. And it provides an opportunity to create a cheap and simple and very effective multifunctional optical elements for sub-wavelength optics. I will skip possible application. There are plenty of them. These diagrams were experimentally verified, mimicking the scattering by light, by scattering of electromagnetic radio wave of centimeter in a centimeter range. This is the feature of the experimental setup, and we get excellent agreement with the calculated diagram. So this is outside the scattering. What is inside? Similarly, we have large polarizability, then we have large mobility of the bound charges, then we have at higher frequency, the electron becomes equivalent to a conductor, and then it seems that induced field should compensate the applied field, and we should have zero field inside the particle. Is it the case? No, this is not, because we have forgotten about the polarity resonances. If the refraction index tends to infinity, then the wavelength inside the particle tends to zero, and inevitably we have the resonance conditions fulfilled. Then the particle becomes a resonator, and instead of zero field with weak dissipation, we have strong field, very strong field inside the particle. This is the example of this field. And this is non-magnetic particles, but the magnetic field is enhanced in this. This is the exact solution for real problem, for real material parameters. And we have 4,000 times enhancement of the magnetic field inside the particle at the resonance. And we have also controllable contrast of the field inside the particle. This is very important for nonlinear applications. This is the estimate. We could see that the corresponding components of the magnetic and the electric field, the ratio is about square root of epsilon. And this is a large quantity. So the magnetic field is much larger than the electric field. And basically we have tangential component, and the radial components are small. Experiment. We did the same experiment. We measured the field inside the particle, but the particle is liquid. So we used liquid dielectric with the proper dielectric constant. And again, we made the experiment with radio wave frequencies. And this is the measured pattern. On the left, we have the calculation. On the right, we have the experimental results. You could see excellent agreement of them between them. And we could achieve the enhancement of the magnetic field about 350 times. Dynamic resonance. So if we have a resonance scattering with higher quality factor, then we have a long transient to steady state. And if we have a difference of different modes, then with different Q factor, we could have a transient pattern. And then we can have some effects which exist only during the transient period and does not exist at the steady state scattering. And the characteristic times now lies within the framework of modern experiments. So it is experimentally feasible effects. So as an example, I consider light scattering by a cylinder and Fano resonances. Fano resonances is the interference of the mode with the same multipolarity, for example, dipole modes, with two kinds of submodes. One is related to surface excitation, and another is related to the bulk excitations. And then the interference of these two submodes, depending on their phases, could result either in their enhancement or in their suppression. So then we are selected the cylinder. This is a germanium cylinder, again, the actual material parameter, with this value of the size parameter, where we have two destructive Fano resonances related to two modes situated close to each other. So then we model the scattering by direct exact solution, direct numerical solution of the complete set of the Maxwell's equation. And then this is a rectangular pulse. And this is the result of the numerical calculation. You could see the transient, which is characterized with large spikes, which are suppressed at the steady state scattering. An interesting case is the spike behind the trailing edge of the pulse, because we do not have any radiation, incoming radiation, but we have a strong scattering. This scattering is related to energy release, and the energy at this stage, the energy accumulated during these previous stages of the scattering is released from the particle when the incident wave is over already. And we developed a certain integrable model which describes this phenomenon very well. And the last thing I want to stress is that the dynamical scattering is characterized by the changing of the direction of the scattering, directivity. So, excuse me. Well, this is the movie. You could see how it looks like. And so on. I didn't have time to show you all movie. And there are three characteristic snapshots of this movie. And you could see how drastically the scattering intensity changes during the transient period. And all scattering radiation is confined in a small solid angle. So actually, this is a very directional scattering. And this is a nanolaser, very simple nanolaser, which consists just a single particle without any invariant population. Okay, conclusions. At resonant light scattering by subwavelength plasmonic particles with a small dissipation rate, the non-dissipative radiative damping plays a dominant role. In this case, the scattering is anomalous and has very little in common with the conventional relay case. At the anomalous scattering, there is a funnel in the Poynting vector pattern. The funnel collects the incident radiation from a large inlet downstream and conveys it to the immediate proximity of the scattering particle. The subwavelength near field pattern of the Poynting vector exhibits various types of singular points whose types and positions are susceptible to the frequency of the incident wave. A resonant light scattering by a subwavelength high-index electric particles with a low dissipation rate may be employed to create tunable scattering diagrams. This effect may be a basis for designing and fabricating a new type of simple and very cheap multifunctional optical nanodevices. This scattering may be accompanied by a huge electromagnetic field concentration within the particle, which is important to enhance nonlinear effects. Notably, the enhancement of the magnetic field in non-magnetic particles is about square root of epsilon times larger than that for the electric field. The field pattern within the particle has a tunable contrast. The tuning is achieved by varying the frequency of the incident wave. There are main publications and funding. And finally, I thank you very much for your kind attention. I am open for questions, if any. Thank you.
Thank you very much for your presentation. It was very interesting, and now it's open the time for questions. And so the audience is invited to ask to Michael some questions. Very interesting presentation. Well, if there are not questions, I can proceed to call the next speaker. I call up Gurnalnik Institute of Automation and Control Processes, Russia, to deliver a speech on two innovative paradigms on film growth: perfect magnesium silicon film for light and heat conversion into electricity. Is it there, Gurnalnik? We cannot hear you.
Unmute your mic.
Yes, Michael, if you can, don't share your screen and let's enter to Alexander. Alexander, we cannot hear you. Maybe it is because Michael is still in there. Thank you very much, Michael.
No, my screen shouldn't be shared. I switched it off. Do you see my screen still?
Yes, yes. Well, in my case, yes,
It's
I'm
strange.
seeing your.
So something is wrong. So let. Yes. Okay.
Could we take a few seconds just to the program?
Okay, so then now it's okay, right?
Yeah. Thank you very much. Alexander, we cannot hear you. I will chat with him.
Okay.
Okay.
Can you hear me now?
Now, yes.
Okay. And can you see my screen?
Yes, we can.
But I can't. Unfortunately, I can't see my own presentation.
Take your time.
Okay. Okay. Good morning. I'm Alexander Guralnik from Vladivostok. By the word, now it's deep evening in Vladivostok. It's 8 in the evening. First of all, I would like to express our deep gratitude to the organizers for the possibility to present our report to you. I'll report about two useful experimental methods developed in our laboratory and illustrate these methods by recent results related to synthesis of magnesium silicide on hot silicon surface. Can you hear me? Okay.
Yes.
This is the plan of my presentation, and I'll begin. Many modern technologies include different temperature-dependent processes, and many experimentals are carried out to find the optimum parameters for these processes. And if we manage to obtain the whole range of temperatures on one sample, it can reduce the necessary number of experiments significantly. And in our laboratory, we use low resistivity silicon substrates attached between tantalum clamps. If such substrates are heated by direct current, due to the Peltier effect, the significant difference in temperature between two ends of the sample can occur. And if the resistivity of the sample is really low of this order of magnitude, we have to use very high values of current, and the Peltier effect becomes quite significant. Due to the Peltier effect, if the major carriers are electrons, then due to the Peltier effect, the positive end of the sample becomes heated, and the negative end is cooled by the Peltier effect. And now I briefly list the most natural fields of investigations where this phenomenon can be naturally used. As a matter of fact, all the dependencies on temperature transform to the dependencies on coordinate on the sampled surface. So if we, for example, if we study diffusion, it's well known that the diffusion coefficient depends on temperature. And it's sufficient to measure the diffusion depth in a few different points throughout the sample. And we have the dependence of the diffusion coefficient on temperature. It's very simple. As well, many surface or interface reactions depend on temperature. And if we measure the reaction product in a few different points throughout the sample surface, we obtain the dependence of the reaction rate on temperature. It's quite natural if we study phase diagrams that take place at some particular temperatures. It's quite natural to use this phenomenon in such investigations. And many other physical properties which depend on temperature can be naturally used in this way. And the number of the necessary experiments can be significantly reduced. Another very useful experimental approach is pulsed deposition. Sometimes it's necessary to vary the deposition rate within very wide limits. For example, in our laboratory, we can achieve the deposition rates as high as a few hundred of nanometers per second, or just a few tens of thousand nanometers per second. This is realized in a very simple way. This is the scheme of the simple device used in our laboratory. This is the two-stage evaporator. At the first stage, the necessary substance is slowly and in a very controllable way deposited onto the surface of a very thin tantalum foil. And at the second stage, a powerful pulse of current instantly hits the foil, and the substance is evaporated and deposited onto the substrate. The necessary powerful current pulse can be produced, for example, in a very simple way. Just discharge the large capacitor through the foil. The foil is very thin, so it has very small mass and very low inertia. It can be heated really instantly. In our experiments, we used the dose of deposition from 1 nanometer of substance up to a few thousand nanometers. And the duration of the pulse can be from 10 milliseconds up to a few hundreds of milliseconds. We used this approach to tune island concentration on the silicon surface. For example, because the concentration of islands on the surface depends on the ratio of the deposition rate and the diffusion coefficient. The diffusion coefficient can be controlled by the substrate temperature, and the deposition rate can be controlled by the foil temperature and the amount of the material pre-deposited onto the foil. And I'm going to demonstrate you a real-time process of self-propagating high temperature synthesis initiated by pulsed deposition. To illustrate the results that can be obtained by these two methods, I'll describe two experiments with synthesis of magnesium silicide. This material is very perspective because it has a high absorption coefficient in the near infrared range, really rather high. And thus it can be used in solar cells. As well, it has a rather high figure of merit, so it can be used in thermoelectric devices. It is the only stable phase in the phase diagram, so it can be naturally integrated within the silicon-based technology. And what is very important nowadays, both magnesium and silicon are abundant, cheap, and quite ecological materials. So, in our opinion, these features make this material quite competitive to, for example, perovskites, very popular now, despite they often are very toxic. Nevertheless, there are problems in synthesis of magnesium silicide because at low temperature it does not intermix with silicon and silicide doesn't form. But at high temperatures, the deposited magnesium immediately evaporates without formation of silicide. So this leads us to the idea of using ultra-fast deposition, pulse deposition, as possible solution. In our experiment, we used a sample. We used both the methods described above. So there was a gradient of temperature on the substrate surface, and we used the pulsed deposition of magnesium onto this silicon substrate. The deposition rate, I must say, the average deposition rate was about 7,000 nanometers per second. Of course, at the beginning of the pulse, it was lower, and at the end of the pulse, it was much higher. The duration of the pulse was about 50 milliseconds, and the deposition dose was 370 nanometers of magnesium. This is the picture of another sample, of course, because at these temperatures, the sample looks cold, because at these temperatures, it does not irradiate the visible light. And this is the short movie of the self-propagating reaction launched by the pulse deposition. Oh, sorry, I must say that it can be naturally expected that the exothermic reaction between magnesium and silicon will be more intensive at the hotter end of the sample. And the reaction front will propagate from the hotter end towards the colder end. And this is the movie, the real-time process. And this is the same in slow motion. You can see that the front propagates from the hot end towards the colder end. And again. again, slow motion. So you can see that the self-propagating high temperature synthesis can be launched by instant supply of one component onto the surface of another component. As a result of this process, we obtained the sample, which its photo you can see here. You can see that only some part of the sample is covered with the magnesium silicide. And we studied this sample by means of Raman scattering, Raman spectroscopy, and these are two spectra taken from two different parts of the sample. The black curve corresponds to the point with the temperature of 400 Celsius during the deposition pulse. And the gray curve corresponds to the point that had the temperature of 480 Celsius. You can see that the gray curve has the peak corresponding to the silicon, crystalline silicon. That means that at this point, the thickness of the silicide is small and the substrate irradiation can penetrate it. So, since the distribution of temperature is continuous, in one experiment we obtain the exact value. This is the precise limit. For colder temperatures, the process takes place, and for higher temperatures, it does not. So we immediately find the exact value. With other methods, it would be necessary to use many experiments for this result. And now another experiment. We already had the reasonable temperatures for growing magnesium silicide. So we chose the substrate with very high resistivity. So the Peltier effect did not take place. It was negligible. So the temperature was uniform throughout all the sample. It was 340 Celsius. And the magnesium dose in this experiment was 700 nanometers. The duration was longer. It was a few hundreds of milliseconds. And we used the pulse deposition onto the hot surface. And as a result, we obtained a film with a practically perfect crystalline structure. You can see that there are only this is the diffractogram of the taken from the sample. You can see that there are only 3 peaks corresponding to the planes 111, 222, and 333. And all the other peaks belong to the silicon substrate. So the film is really perfect. This is the electron microscopy image of this sample, and this is the transmission electron microscopy picture. You can see the columnar structure of the film. This is quite typical from our previous experiment. We knew that the columnar structure is quite typical for thick films of magnesium silicide, but other experimentalists could not obtain such films. Here you can see the high resolution image, and you can see that fast Fourier transformation shows that it is that the film has good crystal quality. And this is the elemental distribution, element distribution in the depth of the film. You can see that the upper layer of the film has much oxygen. The green curve corresponds to oxygen signal obtained by energy dispersive spectroscopy. This is the signal of magnesium and the signal of silicon. But you can see that in the depth of the film, the oxygen signal saturates, but it is not zero. So we obtained the unintentionally doped our film with oxygen. And as a result, we obtained a quite unusual, rather unusual film, because it has p-type conductivity. So the holes are the major carriers in this film, and it has very high electrophysical properties. For example, the carrier density is very high. The mobility is very high. For example, at room temperature it's quite high, and the conductivity is very high. The gray curve corresponds to the literature data for the similar p-type magnesium silicide obtained in other experiments. We found it in literature. So the material of our film has, for example, conductivity about more than two orders of magnitude higher than the reference sample. And this is the model of the silicide formation process obtained in our experiments. You can see that if the temperature allows to accumulate large population of magnesium atoms on the silicon surface, if they don't re-evaporate very fast, magnesium silicide nucleates, and the lifetime of the deposited magnesium atoms on the silicide surface is not so short as on the clean silicon surface. So magnesium accumulates, and magnesium film grow on the surface of silicide. And we have the typical solid phase reaction between magnesium and silicon, launched by the pulsed deposition. So this is the physical model of the process. This is the brief summary of our report. Thank you for your attention, and I'm ready to answer your questions.
Thank you very much for your presentation. It was very interesting, and I am sure that there are some questions from the audience. The open time for questions is now, so you are invited. In the case that there are no questions, we invite you, Alexander. We thanks again, and we invite that you can don't share your screen. In order to proceed.
Thank you.
Okay. You're welcome. In order to proceed with the next talk, now we have the big pleasure to invite Raman Singh, Monash University, Australia, to deliver a keynote speech about graphene coating, a disruptive approach to remarkable and durable corrosion resistance of metal and alloys. So, if Raman Singh is there, you are invited to.
Yeah, I'm very much here, but I think other speaker or somebody has to stop sharing the screen to enable me to be able to.
Sorry.
Yes, it's okay. We take the few minutes, the time that it is needed in order to set up the other presentation. Sometimes take time, few seconds, just.
All right. Yep, I got it. Yep, I'm waiting.
Okay, we are there.
I'm getting a message. You cannot start the screen share while the other participant is sharing. So one of the participants is still sharing the screen.
Yes, well, I'm watching as well.
All right, I'm waiting for your instruction. When you say ready, I will start. Thank you.
But
yes,
can you,
Alexander? Can you switch off your share screen using the same key?
I am trying. Actually, I am trying.
Okay, that's okay. It's okay. Okay. Raman, can you wait a few seconds? We are waiting to Alexander.
No problem. I'm waiting. Don't worry. I'm waiting. As I said that when you say start, I will start. No problem.
Okay. Yes, it is. So sometimes take time to do the right click and moreover the reaction of the whole system. It could be give us some delay, but it is not. We are on time.
Just to give you a hint, if you are the host, you have the ability to use the stop sharing screen. Anyway.
Yes, it could be, but
actually I can't find the necessary button.
Okay, you have in the middle, right on the bottom of your screen, you move your click up and down, and it will appear a rectangle with different function, and in the middle you will have share screen. You have to click another.
I think it's working now. That's fine. It's done.
Okay. Yes. It was changed. So Raman Singh, you're welcome.
All right. Can you see my screen?
Yes. Yes, it is okay.
Okay. And I'm audible.
I'm really sorry.
Don't worry, Alexander. When I did it, I took longer than you did. Don't worry. So, are you? Am I audible? You can hear me?
Yes, you are audible.
Yes, yep. I can.
Thank you. Okay, let me. All right. What I'm going to talk to you today is about graphene coating as a disruptive approach to corrosion resistance. Before I start, my sincere thanks to the organizers for giving this opportunity to share my research with you people. Can I request people to mute themselves? Yep, thank you. As you can see from the first slide, I'm going to talk about graphene. I will give a bit of brief overview of what graphene is and why we are interested in graphene for corrosion resistance. Why we are interested, first of all, in corrosion, and why graphene, and in between there is the word disruptive, whether what I'm going to present whether it is disruptive or not. I'm from Monash University in Australia. I have appointment between two departments. My formal appointment is as Raman Singh, but I publish as R.K. Singh Raman because before joining Monash University, I had this name as publishing name. Once again, thanks a lot to the organizers. There are a few people who have contributed to this work that has been happening for last 10 years or so. Abhishek Arya had just now submitted his PhD thesis. I have another PhD student working on this topic with IIT Bombay, with whom Monash University has very strong research program. After that, the three names, Sanjeev, Anisur, and Abhishek, they were PhD students. Others were also PhD students, but they just contributed to the work that I'm going to present. There are a couple of undergraduate students, which is very interesting. Mainak and Parma are my colleagues. First samples for this work came from Professor Ajian's lab in Rice University. He is one of the leading scientists in the domain of graphene or 2D materials. Why corrosion? Because corrosion is a very expensive affair. About 4% of the GDP of any developed country is lost because of corrosion. So it is extremely expensive affair. As a matter of fact, a developed country like USA loses about $300 billion every year because of corrosion. And I must qualify that statement by saying that when you take everything associated with corrosion into account, like you have to use stainless steel, you have to have coatings, and all those expenses put together indeed turns out to be $300 billion or even more. Because corrosion has been old phenomena, people have been doing variety of things for addressing the problem of corrosion, like developing corrosion-resistant alloys. I talked about stainless steel just now. But even the best of the corrosion-resistant alloys, like duplex stainless steel or super duplex stainless steel, they fail when corrosive environment is highly demanding, like desalination plant, where you have highly concentrated chloride solution in the desalination plant, or the metallic containers for nuclear waste, which has to perform for hundreds of years. Even the best of the alloys fail to perform under those kind of demanding situations. Other approach is to have coatings, like you have coating on your car or coatings on your frying pan or whatever. But there is no such thing called everlasting coating. Every coating eventually fails. So what I'm trying to get at is that people have done a variety of things for addressing the problem of corrosion for two reasons. One, because it is very old phenomena, and more important feature is that it is very expensive phenomena. So people have done a lot of things for addressing the problem of corrosion. Why I'm emphasizing that is because of that reason, doing something disruptive, doing something entirely new, disruptive is very challenging because people have explored almost everything. But if you could do something successfully, something disruptive and also successfully, it will be commercially very rewarding because corrosion is very expensive affair. Just to give you a flavor of what I'm going to talk to you about is there on this slide, that if you take a piece of bare nickel and you expose it to corrosive solution like seawater sodium chloride, it will be destroyed like this. As you can see, that heavy corrosion attack on the surface of bare nickel. But if you coat it with graphene, the topic of my talk today, you will find that there is very little corrosion. Whatever white spots you see here, they are just solidified salt, not corrosion spots. So that's the kind of thing that I'm going to talk about. What is graphene? We know what is graphite. Graphite is the layered structure shown here, that you have many layers of organized carbon atom in each layer. And you have a stack of that, and then you have, if you have more than 10 layers, we start to call it graphite. And it is, each atom is sp2 hybridized carbon atom. It is 2D honeycomb type of structure, and it's layered structure. When you separate one single layer from that aggregate, it is graphene. One single atomic thick layer is graphene, And if you did that before 2009 and you understood the physics of this layer, you would have won Nobel Prize. That's what happened. The Nobel Prize was given exactly for that in 2010. And if you make a ball out of this, then it is buckyball, which was also given Nobel Prize. If you make a tube out of it, that's carbon nanotube, which missed getting Nobel Prize. Talking about properties of graphene, it has extraordinary properties when you talk about properties like conductivity, whether it is thermal conductivity or in-plane electrical conductivity. It is really a couple of orders magnitude superior to any metal. So graphene has a few or quite a few extraordinary properties. I will talk about the properties which are relevant for our talk, that is corrosion and graphene as corrosion-resistant coating. First one is mechanical property. The graphene is very strong. In fact, for the same thickness of the material, graphene is about 100 times stronger than the strongest steel. Generally, when you have a material which is very strong, its toughness is poor. Like ceramics is very strong, its toughness is poor. But graphene is one material which has both strength and toughness. Now talking about the chemical properties of graphene, like if you have any coating, the coatings degrade because of reaction with environment. In the case of graphene, it is very resistant to chemical attack. Even a very aggressive chemical like hydrogen fluoride will not attack graphene. Other aspect is impermeability, the corrosive environment, whether it can permeate through coatings. Most of the coatings fail because they have pinholes, defects, and corrosive environment permeate. They migrate through the coating and they cause problem of corrosion to the metal substrate. In the case of graphene, the little hole that you have in the middle of hexagon is so small that even helium can't pass through. Helium is the second smallest atom in the periodic table. Even helium can't pass through this little hole. So the species that cause corrosion, like water, like oxygen, like chloride, they will not have any chance of passing through this because those entities are much larger. The chloride ion or oxygen or H2O are much larger entities as compared to helium. So they will not pass through this. So when it comes to impermeability of environment or permeability of the corrosive environment through the coating, graphene is in fact extraordinary. And people have done experiments. I don't have time to go through the details where they have shown how the graphene coated area form bubbles rather than the gas passing through the material. So what I showed you just now is that graphene is very impermeable. It is both strong and tough, and it is very inert. There is no single material which has all these properties available in one material. And that's why the question whether graphene can be an ideal corrosion barrier coating. Okay, and that's where is the interest in this material. I will begin with our just published paper, just published early this year. And what I'm trying to show you is that I'm trying to compare the graphene-coated nickel and the bare nickel. So nickel without graphene coating and with graphene coating. But more importantly, I'm trying to compare the corrosion behavior in different types of environment, highly aggressive acidic environment, highly alkaline environment, and neutral chloride type environment. And for those who are not from corrosion field or electrochemistry field, just to let you know that the intercept of these two arms of this plot, which is potential, electrochemical potential versus current density plot, the intercept of this plot tells me the corrosion resistance. So this point gives me corrosion resistance. What I'm trying to emphasize here is that irrespective of the environment, whether it is highly acidic environment, highly alkaline environment, or neutral environment, neutral corrosive environment, the corrosion resistance of graphene-coated nickel is same or similar. You can see that magnitude of current, the current is the indicative of corrosion, is same. It is same irrespective of the environment. So graphene is such a that it does not care about the aggressiveness of the environment. Whereas if you have bare nickel, you can see that bare nickel without coating, it corrodes at much higher rate. In sulfuric acid, it doesn't corrode at such high rate in alkali environment because alkali passivates it quickly, and in chloride environment it has mixed or in between type of behavior, right? And this is a log plot. So the very thin coating of graphene on nickel improved corrosion resistance in sulfuric acid environment by 2 orders of magnitude, by 100 times. It's a log plot. And that's what I'm trying to show here. And also the post-corrosion morphology observed under scanning electron microscopy showed the morphology which complements the corrosion data. The first paper on the topic of graphene for corrosion resistance came from Rod Ruoff's group when he was in Texas. And what he showed is that he took a piece of copper, coated it with graphene. So Cu plus G is graphene coated copper. Also, he took some copper nickel alloy and coated with graphene. And he exposed all of them to air at 200 degrees Celsius. And you can see that graphene coated samples, whether it is alloy or pure copper, it did not show much change in color, not much oxidation. But if you have uncoated copper, it oxidized, formed cupric oxide, which has this color, or the copper nickel alloy also oxidized and it changed the color to what you see here. So graphene, this was the first ever demonstration of graphene giving corrosion resistance. What the same group did is that they also coated a penny with graphene. Only upper half of the penny was coated with graphene, lower half was left uncoated, and they dropped the penny in a highly corrosive hydrogen peroxide solution. And they found that upper half, which was coated, did not undergo much corrosion. It was shiny as in the beginning, whereas the lower half, which is not coated, tarnished and underwent corrosion. Ours was perhaps the first systematic work done by corrosionists on the corrosion resistance due to graphene for copper. And for this copper coated with graphene, those samples we got from Professor Ajay's lab, both coated samples and uncoated samples, graphene coated one and uncoated one. And first of all, we had to ensure that what we got was actually graphene coating. And how do you do that? You do it by Raman spectroscopy. And when you do Raman spectroscopy on the sample which was subjected to CVD, chemical vapor deposition for graphene coating, you can see that it had typical peaks for graphene. What are those typical peaks? This G peak and 2D peak. These are the typical peaks for graphene. When you have these two peaks, you can say that you have graphene or graphene-based material in your sample. And we also have this D peak, which is for the defects in the graphene coating. So the graphene coated copper did indeed show the peaks for graphene and some defect, whereas the pure copper didn't have those peaks. So the presence of these peaks give you confirmation of presence of graphene, but they give you another important information. For a single layer graphene, the G peak is shorter, is dwarfer compared to the peak. So as you increase the number of layers, you can see that G peak becomes taller and taller. And as a matter of fact, the ratio of the intensity of G to 2D peak, it gives you number of layers. Okay, so keep that in mind, and we will use that later. So we had graphene coated copper and bare copper samples, and we did again the polarization test in an environment close to seawater, concentrated sodium chloride solution. And you can see that once again, the intercept of these two arms gives me corrosion resistance. It's just that I have changed the axis. You can see that graphene coated copper showed 2 orders of magnitude, more than 2 orders of magnitude superior corrosion resistance as compared to bare copper. I emphasize that we had single layer graphene. You can see that G G peak is shorter compared to 2D peak. So one atomic layer thick graphene giving corrosion resistance or improving corrosion resistance by 100 or more times, more than 100 times. And that was confirmed by another technique, which is called electrochemical impedance spectroscopy, where the impedance value at the lowest frequency gives you corrosion resistance. And once again, you see that graphene-coated copper showed impedance 2 orders of magnitude superior compared to uncoated ones. And we did post-corrosion characterization of the morphology of the specimens, and you can see that graphene-coated one didn't have much corrosion. Whatever dark spots you see is because of folding, not because of corrosion product, whereas here, the uncoated copper underwent severe corrosion and formed cupric oxide. That's why this dark color. Around the same time, people also started to work on this topic. There was a work from a group from United States. They showed improvement, but by maybe 10 times improvement, less than an order of magnitude. And there was another work from Monash University itself who showed not much improvement at all. So what was going on here? There may be some students here, so I should emphasize here, it's all right to say that, look, our samples or our work showed maximum 2 orders of magnitude improvement. Others could not show we are the best. Okay, that may be true, but a good researcher will always try to know why we are getting such a good result, why others are not getting good results. So when I say good researcher, I mean my team, not necessarily myself. But anyway, so at that time we had this great variation in results, and we were getting a bit puzzled about this. As if that was not enough, we started to get some interesting papers. This paper, published in a very reputable journal, shows that graphene, as a matter of fact, accelerates corrosion. Means corrosion resistance of the graphene-coated copper is poorer compared to that of uncoated one. Very interesting. As if one was not sufficient, there was another paper published in the same prestigious journal, and you read the title, interesting title, Graphene as a Long-Term Metal Oxidation or Metal Corrosion Barrier, Worse Than Nothing. If you have no coating, you are much better off. That's what this paper is saying. What they did not see, that same paper did not see that wherever graphene was intact, corrosion was, as a matter of fact, intact there. So the problem was not with graphene, problem actually was with the type of graphene or the poor quality graphene they could develop on copper. And they did in fact say that wherever graphene coating was discontinuous, corrosion happened at that location. And which is consistent with what we had already said in our publication just a year ago. As I said, that ours was just the second ever publication on this topic. And in this paper, we clearly said that if you do not have continuous layer of graphene on copper, it will, as a matter of fact, make the corrosion resistance poorer. And that's what was exactly happening in those two papers. And it has a basis in the very fundamental electrochemistry. Graphene or graphite is the most cathodic material. It is highly cathodic. What it means is that when it is in contact with any metal, like copper in this case, it will force copper to corrode at higher rate. And that's what was happening, that wherever there is disruption, and there were too many disruptions, so corrosion was happening at very high rate. And that's why corrosion was getting accelerated because of graphene. Something similar was also seen in the first paper on this topic by Rod Ruoff's group, where they could show graphene corroding or the oxidation happening at the vein boundary, that is, the boundary where two graphene domains met for the same reason. So the inter-domain boundaries or discontinuities are the areas of problem in the case of graphene. And as you can see here, that those inter-domain boundaries are not the only problems with graphene. There are other problems. When you develop graphene on metal, they invariably develop some wrinkles. And why they develop wrinkle, it is very interesting. Graphene happens to be one of the very few materials which has negative coefficient of thermal expansion. What does this mean? That when you cool it, it expands. Most materials contract when you cool. So after CVD, chemical vapor deposition at high temperatures like 900 to 1000 degrees Celsius, when you cool down, graphene is expanding and metal underneath is contracting, and it gives lead to wrinkles. And those wrinkles are not good because people have shown that corrosion can happen at the locations of wrinkles because there can be cracking happening at the top of the wrinkle, and corrosive environment, oxygen in this case, can penetrate through this, and people have shown that wrinkles are not good. The corrosion can happen at wrinkles. So what I showed you is that there are defects in graphene film that you develop on metal, defects like you have inter-domain boundary where corrosion can happen at high rate. You can have point defects. In place of hexagon in the graphene film, you can have pentagon, you can have heptagon, and those are point defects. You can have wrinkles. I just now showed you. You can have wrinkles. You can have ripples, and all these agencies are defects which can cause corrosion. And that's the time when my first PhD student joined to do PhD on this topic. And you can realize how nervous he will be, because there were 2 papers published in very reputable journals saying that graphene coating corrosion resistance is worse than nothing. So he said, am I going to kill my career by working on this topic? I said, look, let us investigate and we will find what they are saying is correct or not. And that itself is PhD, so don't worry. Between 2 of us, we came up with one hypothesis, that the problem is because of discontinuities in the graphene coating. How if we develop multi-layer graphene? If we develop multi-layer graphene, the discontinuity in the first layer is likely to be masked. Why we took this approach is because we quickly realized developing a discontinuity-free single layer is almost impossible. And when you have commercial equipment, they will have large surface. Can we develop single layer graphene without any discontinuity? Answer was no. So why don't we take alternative approach? So hypothesis was to develop multi-layer graphene so that the defects of the first layer could be masked by subsequent layers, and we could show that whatever wrinkles were there in the inner layer, they were masked by upper layer. Upper layer themselves may have wrinkles, but it is unlikely that where you had wrinkles in the lower layer, you will have wrinkles in the upper layer as well. So just simple masking, very simple hypothesis. And with that, we started to develop graphene. I will spend just less than a minute to show how we develop graphene by chemical vapor deposition. What we do that we first have this sample of copper or nickel placed here, and then at high temperature, we supply hydrogen with the help of argon as carrier gas. And what does hydrogen do? That if you have any native oxide, and there will be native oxide invariably on most metals. So if you have native oxide, that oxide will be reduced by hydrogen. So suppose you have cupric oxide, CuO, it will be reacting with hydrogen to give you Cu plus H2O, so that layer of oxide is removed and you have pristine layer of copper, and then you supply hydrocarbon. If you supply hydrocarbon at a right partial pressure, at right flow rate, then that hydrocarbon will split in carbon and hydrogen, and that carbon can deposit as graphene. If you did not maintain right partial pressure, you can have diamond, you can have carbon nanotube, you can have carbon soot, you can have whatever. So, so maintaining right partial pressure is very important, and that's how we develop graphene on metallic surfaces. I should also quickly tell you that we use copper and nickel as a substrate, mainly because, as I said, that substrate acts as the splitting of hydrocarbon happens on the substrate, because copper and nickel are very good catalysts for splitting hydrocarbon. Chemical engineers will tell you that that's true. But development of graphene and mechanism of that is entirely different in the case of copper and nickel, for a very simple reason, because copper has very, very low or insignificant solubility of carbon. So whatever carbon is generated here because of catalytic dissociation of hydrocarbon, that produces graphene straightway. That arranges itself to produce graphene straightway as long as your carbon supply or carbon partial pressure hydrocarbon partial pressure is right. So that's the mechanism for formation of graphene on copper. About nickel, it is different because nickel has very high solubility of carbon. So whatever carbon is produced, it diffuses into the metal, and when you cool it from the CVD temperature, when you cool down, then solubility decreases, carbon is rejected to the surface, and it produces graphene. Here, in the case of copper, you can produce at the best 2 layers of graphene, because the places where where you have graphene coating developed, catalytic action stops there. So you can produce 1 or 2 layers of graphene. Whereas in the case of nickel, you can produce multi-layer graphene, and which is attractive because if you have more number of layers, then the masking effect, as I told earlier, will be more effective. So with that understanding, we started to develop our own graphene using our own setup that I showed you earlier. But the graphene that we developed was of poor quality. You can see the D peak is very tall. The D peak is for defect, so it's very tall. But it was multi-layer graphene because G peak, you can see, is taller compared to 2D peak. And with this, we could achieve some improvement in corrosion resistance, not huge, maybe 10 times improvement, not as good as earlier because our quality of graphene was not as good as earlier. But the purpose of this study was to show whether we have durable corrosion resistance. And for that, we did, again, the electrochemical impedance spectroscopy. As I told you, that impedance at lowest frequency gives you idea about corrosion resistance. And you can see that for up to 400 hours, we did testing in sodium chloride solution, and there was no change in corrosion resistance. So the point that I'm trying to get across to you is that if you develop multi-layer graphene, which addresses the problem of discontinuities in the graphene coating, you have corrosion resistance to be durable. You have durable corrosion resistance that we could show for the first time, and it gave the student quite a lot of confidence that if you do systematic work by understanding the shortcomings in earlier work, you can address that problem. Subsequently, we worked further on improving the CVD parameters, and we could show that that coating that we developed, it could give corrosion resistance for times greater than 1,000 hours. You can see that uncoated copper will be destroyed, whereas graphene-coated copper was giving considerable corrosion resistance even after 1,000 hours of exposure to sodium chloride solution. So at this stage, we started to look into what were the issues. Developing defect-free graphene is challenging. It's impossible. Not having discontinuity, it will not be possible. So far, we had developed graphene on copper and nickel or copper-nickel alloys, but can we develop graphene on alloys or materials which are of more common use nature, like mild steel? And that's what we will be talking about in the rest of the paper, the rest of the presentation. Now, as I said, that we started to work on improving the processing parameters. And I will be talking about the critical parameters. One was that after the CVD, if you do rapid cooling, that's advantageous. If you do cooling under the environment without hydrogen, that's advantageous. So under this optimized condition, we developed graphene with less wrinkles. And as I told you earlier, wrinkles are deleterious. As opposed to that, if you did slow cooling and with hydrogen in the environment, you could not even produce graphene, as it is clear from this Raman spectroscopy plot. Whereas in between, if you did rapid cooling, but still you had hydrogen, you did produce graphene, but it had lots of wrinkles, lots of defects. So with this best optimized condition, we started to do some more work, and we showed that yes, indeed, the graphene that was produced with rapid cooling and without hydrogen gave considerable improvement in corrosion resistance, as you can see there. But what was most important was that corrosion resistance that we got, and when it stabilized after the initial period where little bit of pores, they are filled up with the corrosion product and all that, then when it stabilized, that stabilized corrosion resistance lasted for more than 1,000 hours. And saying that it only lasted for 1,000 hours is not correct, because the trend is such that there is no reason not to believe that it will not last forever. It can continue. It is statistically proven data. As you can see, We have also included the scatter in the data, and it will continue to give corrosion resistance for a long time and possibly forever because of those great properties of graphene. Whereas if you did not have a good quality graphene because your processing parameter was not correct, like you have rapid cooling, but with hydrogen, you have lots of wrinkles, and that graphene did not give good corrosion resistance. And so was the case with nickel without graphene coating is about 2 orders of magnitude inferior in corrosion resistance as compared to the graphene coating developed with the right parameters. With that, and this you have seen already, that graphene coated nickel with the right parameter, rapid cooling without hydrogen, produced graphene which gave very good corrosion resistance for more than 1,000 hours, and that's fine. Then we started to work on
Dr. Raman.
Yes.
We are on time. We are on time.
How much time do I have?
30 seconds, 1 minute, no more.
Okay, right. I will finish in 1 minute. I will go quick. Fine, no problem. So what we started to show is that if I have a tilted surface, it produces better graphene. Like you have tilted surface, it produces better graphene, as you can see, compared to if you don't have right tilting. We proved it by Raman spectroscopy that if you have right tilting, it gives more uniform graphene. And we showed that corrosion resistance also was very good. This is at 45-degree tilting. You can see graphene is still intact, and that gives corrosion resistance for more than 1,000 hours. And then recently we started to work with 3S synchrotron people, and for the first time we used this technique, which is scanning photoelectron microscopy, to show that 45-degree tilting in fact gave very good corrosion resistance, very good quality graphene that gave very good corrosion resistance. We employed the graphene coated nickel for the purpose of using it as bipolar plates for proton exchange membrane fuel cell, and we could show that corrosion resistance was very good. It's also important that here conductivity of the coated material will be important, and we could show that yes, it had very good conductivity. It's a very good material for that kind of fuel cell. Just last 2 slides, that can we develop graphene on mild steel? It is challenging because mild steel has ability to have lots of carbon at higher temperature, at 1,000 degrees Celsius. When you cool down, it starts to reject so much carbon that in place of graphene, you will start to develop carbon soot or so much. So that's the technical problem. Also, iron is not as efficient as a catalyst to split hydrocarbon. But good news is that we managed to develop, this is last slide, we managed to develop graphene on mild steel by some suitable surface modification of mild steel, and that graphene on mild steel gave corrosion resistance for more than 1,000 hours, and you can see that it is consistent, and there's no reason that it will be everlasting. Why it will not be everlasting? So graphene coated mild steel after corrosion testing for 1,000 hours, and you can see it is still intact, whereas mild steel without coating would have finished in no time. You can see its corrosion resistance is very poor down here. This has been patented, and we have just now submitted a paper on this to a very high impact journal, one of the top journals of materials, and this work was awarded an award in a competition in Boston. During COVID, we didn't have much time to promote it further, but good news is we were the first to develop graphene on mild steel, which gave long-term corrosion resistance. With that, thank you very much. If there is time, I'm happy to take questions. Otherwise, thanks a lot again to the organizers for the opportunity, and I'm happy to answer questions.
Thank you very much for your presentation. We are on time. We don't have time for questions, but there are some questions there with up in hand. You can contact directly to Raman Singh via chat. I think that it could be okay. So sorry.
Yeah, please send me an email, right? Raman Singh, Monash University, and you will get my email ID. Please send me an email, I will be happy to answer. Thank you very much. Thanks again for this opportunity.
Thank you very much as well for you. It was a very nice presentation with very interesting results with the dual property of graphene, very interesting. So the next presentation is I call up Thomas Webster, Havai University of Technology, China, to deliver his talk on human nanomedicine, nanomaterials in the clinic. Thomas, are you there?
Yes, I trust you can hear me and see my screen.
Yes, we hear you well.
Great, excellent. So thank you very much to the organizers for the invitation to present what we are doing in the lab. And I put together a presentation that hopefully you'll find interesting. It essentially talks about nanomaterials in humans and how the field has really advanced over the past decade to really help human health. So we're thinking of getting beyond in vitro animal experiments and actually helping humans with nanomaterials. So having said that, I will be presenting research that has been spun out into a couple of startup companies. So I do need to disclose my financial interest in some of these startup companies that are highlighted on this slide. So I think a great place for us to start to think about nanomaterial use in humans is to really consider what's wrong with our global healthcare system. What is it that we're actually trying to solve? And I guess, unfortunately, you don't have to look very far to find problems in our global healthcare system. I think, obviously, something that's still on everybody's mind is COVID-19. So even though COVID-19 primarily has gone through various parts of the earth and the global population, we're still suffering from SARS-CoV-2 mutations. SARS-CoV-2, of course, being the virus that causes COVID-19. But when I think about 2019, 2020, 2021, 2022, and even the beginning of this year, COVID really highlighted a number of problems in our global healthcare system. I think anytime you have to tell people to stay home in order to stop the spread of a virus, I think you have a problem with the healthcare system. If our only recourse to keep people from getting COVID is to tell them to stop interacting with one another, I think we have to take a hard look at our global healthcare system and fix it fast. So I think what's highlighted on the rest of this slide are other problems in our healthcare system that COVID highlighted. Overcrowded hospitals. We all remember the pictures of a lot of people waiting to get into hospitals for diagnosis as well as treatment for COVID, shortage on ventilators as well as other medical equipment for people who had COVID, severe COVID symptoms. We also had a lot of barriers to entering the hospital, whether in your part of the world it was geographical barriers to entering a hospital, economic barriers to entering a hospital, or even one of the other things that COVID highlighted was psychological barriers, where certain populations, certain ages, whether you were a male or a female, meant that you were more likely to go in to get treatment for COVID. So I think COVID also highlighted psychological barriers that we all have to go into a hospital to see our primary care physician for help. And as you can see, the list goes on. Medical devices, we continue to see medical devices like hip implants, pacemakers, et cetera, that fail and have to be replaced. In fact, during COVID, you might remember elective surgeries were stopped. And that's because the personnel, the medical clinicians who were in planning various medical devices were asked to help with COVID. So we even stopped implanting medical devices for a couple of months, if not a year, during COVID. And you can see the rest of the list: overdependency on drugs to fix everything. We tend to treat every patient the same. in our healthcare system. Certainly, our healthcare system is very reactionary. We do not do enough to predict your problems. And of course, if you're reacting to problems, that becomes inefficient, that becomes costly, and a real problem. So many, many years ago, for all of these problems, whether COVID caused them or highlighted them, or many of these problems existed before COVID, we started looking at nanomaterials, nanotechnologies. In my personal history, in the middle of the 1990s, I started looking at nanoparticles, nanotextured surfaces, nanotubes, to see could this new classification of materials really help solve our healthcare problems. And I think today, in 2023, we don't really have to talk too much about the definition of nanotechnology. I think most scientists certainly know, and I think actually the general public mostly knows the definition of nanotechnology. But how I think of it, of course, is developing materials that have nano dimensions. So a diameter of a particle, length of a tube, a nanotextured surface feature, something that is in the nanometer regime. But importantly, on top of that, part of the definition of nanotechnology to me is demonstrating that there's a reason to make these materials. There's some property that has changed about these materials that make it worth using in medicine. And what we found over the past 25 years, the field has found that yes, these very small materials have very attractive properties in medicine, whether they can penetrate tissues to fight a tumor or kill a cancer cell, whether they can penetrate what's called the blood-brain barrier to fight diseases in the brain. They can penetrate infection to treat bacteria and kill bacteria. Whatever it is, these materials are very small, very reactive, and can promote tissue growth, as well as limiting infection, reduce inflammation, and as we'll talk about, can fight COVID. So that's where I wanted to start in this presentation, was discuss how is nanotechnology being used to fight COVID, and then really my personal journey on how nanomaterials can help fight COVID and hopefully enable us to be better prepared for the next virus that will come along. And there will be another virus that comes along and affects the world. So many of you may know nanotechnology has been at the forefront of preventing the spread of COVID, diagnosing COVID, as well as therapies. And certainly the vaccine that many of us has taken for COVID uses a nanoparticle. So there's many success stories for nanotechnology fighting COVID. Masks, you can buy masks today that have nanoparticles like zinc oxide, silver oxide. These nanoparticles, when they get wet, so if you cough and the virus comes out, SARS-CoV-2, your mask gets a little bit of wet from the mucus, that activates these nanoparticles to produce reactive oxygen species, or ROS. Reactive oxygen species will break down the membrane of the virus. And if you break down the membrane of the virus, you kill it. You basically passivate it and keep it from replicating. We also know that everyday surfaces, you may have seen, many of these surfaces can be coated with nanoparticles. Those nanoparticles also will release reactive oxygen species to kill a virus if it happens to attach to a doorknob, a desk, or an elevator button, everyday type surfaces. And here's a picture of aluminum that's been coated with selenium. Nanoparticles of selenium can be sprayed on surfaces, and those nanoparticles, again, can passivate or kill a virus if it happens to get to your surface. Diagnostic tools. Iron oxide has been functionalized with regions to attach to SARS-CoV-2. You apply a magnet or a magnetic field, you can concentrate that virus so it's easier to detect in a sample, a nasal swab, a saliva sample, etc. But really where I've spent most of my time since 2019 in the COVID area is developing molecules, self-assembled molecules that can attach to SARS-CoV-2 and kill it. So let me show you a real quick video on this idea. The video starts with showing how natural viruses replicate. In case you don't know, a virus enters a cell, releases its RNA or DNA, and divides.
The self-assembled nanomolecule can attach to the virus surface protein. This would keep the virus from attaching to a cell, entering the cell, and replicating.
This is our approach. Basically, as we know, all viruses are nanostructured, so we have to develop materials that are of the same size range as these viruses. Here's the molecule, a cartoon, obviously, of our molecule that we functionalize to attach to SARS-CoV-2. It then envelopes, blankets the virus, keeps the virus from entering a cell. Therefore, the virus does not empty its RNA or DNA and does not divide. This is much different than what other companies are doing. Big pharma companies are basically trying to passivate the virus once it gets into the cell. We think that's a problem because once a virus gets in a cell, it's already started to release its RNA or DNA, and it's already started to divide. We want to keep the virus from entering the cell in the first place because that's how you can maximize the inhibition or keep the virus from replicating. So what is our molecule? Our nanomaterial that we've developed, and we actually developed this molecule before COVID to increase tissue growth, to promote bone growth, cartilage growth, because it's a natural self-assembled material. It mimics many properties of natural tissue. In this work, we basically changed it to serve as a molecule that can blanket or attach to the virus. So here's the molecule. It's basically two DNA-based pairs, guanine and cytosine. That's what the molecule looks like. We functionalize or attach these two DNA-based pairs to each other. For our tissue engineering applications, we put lysine on this molecule. Lysine is an incredible amino acid to grow tissues. Many people who do in vitro cell culture will coat the bottom of their petri dish with lysine because mammalian cells will attach to lysine and grow. So obviously what happens when this building block is added to body fluids, it forms all of these hydrogen bonds, causes these building blocks to link together into a circle. And you can see these active regions, for example, lysine to grow tissues, are sticking out of the molecule, ready to promote cell attachment and ready to promote cell growth. So this basic self-assemble property is what we are leveraging to passivate SARS-CoV-2. So back in 2019, when a lot of my colleagues in China were telling me, get ready, a virus is coming your way, we felt it was our obligation as scientists, as researchers, to develop a molecule that could help in therapy for COVID to passivate SARS-CoV-2. So our very first question was, how do we take this molecule that we developed for tissue growth and adapt it to attach to SARS-CoV-2? Now, one of the big problems we had at this time, again, in early 2020, is my university lab was shut down. A lot of people's labs were shut down at universities. And again, this was because our inability of our healthcare system to keep SARS-CoV-2 in check, to keep it from spreading. So the only recourse was to shut down research labs, shut down universities, and tell people to stay home. I actually think this was a big problem because our research could have been farther along if we had the resources of our lab to test this molecule. But nonetheless, we couldn't get into our lab. We couldn't research ways to passivate SARS-CoV-2, but we did have computers at home. So my research lab, myself, we turned to our computers and we basically used computational modeling, molecular dynamics, if you're familiar with this computational model. What we did, our first step was we examined or we looked up the structure of SARS-CoV-2. Fortunately, at this time, many virologists published on the structure of the first mutation or the first SARS-CoV-2, the Wuhan strain that came out. So we could easily look up what is the peptide sequence of this spike protein? What's the peptide sequence of the membrane protein? And we looked up these sequences and we developed peptides or amino acids that we could attach to our molecule that had a charge attraction to these regions of the virus. So the other important thing we did at this time when we examined the structure of SARS-CoV-2 is we wanted to target a region that we knew would not mutate. If you've been following SARS-CoV-2 and all of the mutations, you know that the spike protein has been mutating. So we don't want to target something that mutates because we're going to have to constantly come up with a new molecule. Instead, the envelope protein of SARS-CoV-2, these proteins that keep the RNA inside of the virus, that has been mutating much less. So we paid attention to the envelope proteins. We developed peptides that had a charge attraction to those envelope proteins. We looked at things like Gibbs free energy, how spontaneous would these chemistries attach and blanket cover SARS-CoV-2. We looked at van der Waals forces, electrostatic forces, and we basically came up with a winner. Peptides that we could attach to our molecule that could then attach to SARS-CoV-2 and passivate it. So our molecular dynamics helped us tremendously during this time period. So this was around early 2020, March, April, and we had a molecule that we wanted to study. Unfortunately, my university lab was still shut down. So I could not study this molecule and how well it could help human health in terms of passivating the virus. So we spun this out into a company. Companies did not shut down their labs. They enabled this research to continue. And we did what was called pseudovirus experiments. Pseudovirus experiments are very safe because the virus is slightly changed to only proliferate once, one cycle. So it dies after it proliferates in one cycle. So it's very safe to be done in a biolevel safety 2 lab or the Audex, which is the company that is commercializing this molecule. They could do it in their labs. So how pseudovirus experiments work is fluorescence intensity shows you the amount of viral replication. The different colors on this graph are the different concentrations of our molecule going from 0 in dark blue up to or down to 1 microgram per ml in light blue. And the other y-axis parameter that's here is the amount of pseudovirus. So going from 10 copies of the pseudovirus, the Wuhan SARS-CoV-2 strain in this experiment, up to 1 million. So we added our molecule, and for 15 minutes, we saw that it passivated upwards of 83% of viral replication. So we were very excited. We thought we were onto something. Then all of the mutations started to occur. So the next mutation that you might remember was the SARS-CoV-2 variant B117. We did the same experiment with the same molecule because remember, we're targeting a region of the virus that doesn't mutate, and we saw upwards of 80% inhibition after just 15 minutes of culturing our molecule with SARS-CoV-2. Variant 501 YV2 was the next variant that came along, spread all over the world, and caused problems. 83% inhibition using that SARS-CoV-2 variant. And again, 15 minutes, same exact molecule. The Delta variant, many of us remember this from last summer, same exact experiment, same high inhibition rates. The current variant that has been causing problems is the Omicron BA2 SARS-CoV-2 variant. And again, we're seeing high inhibition rates with the same molecule. We've also been looking at other viruses. Remember, when SARS-CoV-2 came out, we did not have a molecule that could attach to SARS-CoV-2 to passivate it. So we need to really have a conscious decision to develop molecules that have binding to many different viruses so that we're better prepared for the next virus that comes along. So we've done experiments with HIV, influenza type B, influenza type A, rhinovirus. Rhinovirus is the common cold. In all of these cases, we're seeing the same molecule, our same self-assembled molecule, have strong attachment strength to these viruses. So could this molecule really have versatile binding to a number of viruses to passivate them and keep them from replicating? Of course, I do need to mention to you, anytime you're doing this kind of work, you have to do in vivo validation. We've been working with the FDA to get this in humans. So real quick, an in vivo study where we looked at hamsters. Hamsters is a well-known animal model where we had our molecule subjected to the hamsters intranasally So intranasally is a great route to get to the lungs, where SARS-CoV-2 creates a lot of problem. We saw in this animal study that whether we used our molecule as a preventative measure, so add our molecule first, then the virus, so it's prophylactic, or we use it as a therapy. The virus was given to the hamsters first, and then we added our molecule. We were able to significantly reduce viral load in the hamster. So this was great news. We followed this up with a mouse study that I don't have time to show you, but we're also seeing the ability to reduce viral load in a mouse model as well as this hamster model. So we're currently working with the FDA to get this out there as a nasal spray that could be used for COVID, or it could be used for rhinovirus. Imagine taking a nasal spray to prevent you from getting the common cold. So we're very excited about this research. Just the last thing that I already mentioned about COVID is we have been able to see that Moderna and other companies that have made a vaccine for COVID, they do use nanoparticles, a lipid nanoparticle, to deliver their vaccine. So real success story for nanomedicine. But I do want to emphasize in this talk some other human applications of nanotechnology in the remaining minutes that I have. And really this gets away from self-assembled nanomaterials and into more traditional materials that have been approved by the FDA for human implantation. So our approach over the past 2 decades has been to take medical devices. This is an example of a spinal cage or an amputee device, or maybe a catheter or a vascular stent. Take those devices, figure out a way to put a nanotexture on those devices, and you can improve medical device performance. So you can improve bone growth without using pharmaceutical agents. You can reduce infection without using antibiotics. And in the case of amputee devices that you can see an X-ray here of a rat that received a screw that was anodized to have nanotextures. Here's the exit wound. You can see when those nanotextures are there, you can improve skin growth, attachment, and reduce inflammation. This is all from nanotexturing, not using drugs at all. So this is a real promising area for us. We could talk a great deal about why do these nanotextures increase tissue growth from bone to vascular to cartilage? Why do they reduce infection? Why do they reduce inflammation? And here's some reasons that we have seen why these nanotextures work. One is nanotextures are all over the place in nature. So when thinking about the wing of an insect, it has nanotextures. And the value of this is it's hard to grow bacteria on the wing of an insect. So this insect wing has evolved to have nanotextures which repel bacteria. So we're taking that idea and simply using it in a medical device. We've also looked at finite element analysis. So looking at the mechanical properties of a bacteria membrane, for example, and how the bacteria membrane is too stiff to fit into all of these contours. So what that means is the bacteria does not attach to an implant surface, does not grow, and your immune system is more likely to clear that bacteria. We've also spent a lot of time looking at surface energy. As we all know, nanotextured surfaces, nanomaterials with their greater surface area have greater surface energy. So that interacts with proteins much differently. So one particular protein, fibronectin, is very important to promote bone cell function, leading to bone growth. If you look at these AFM pictures, when fibronectin adsorbs to a nanotextured surface, it stretches out. It's more bioactive. More of it adsorbs because of this higher surface energy. In contrast, over here, when fibronectin adsorbs to a micron surface, it adsorbs in a non-bioactive spherical state. In fact, I don't have time to talk about this, but we've developed an equation where if you give us an implant, we can predict the height, the width, and the length of a nano feature you should use on your implant to improve protein adsorption, which can increase tissue growth, decrease infection, and decrease inflammation. So let me end in the couple of minutes I have left just showing you 3 quick examples of materials that I have worked on in my career that are now in humans. They've received FDA approval and are helping the quality of life. The first one, as I briefly showed you before, is anodized titanium. So if you know anything about anodization, it's an electrochemistry method. You take your implant, like titanium, serves as the anode, you have a cathode, added to an electrolyte solution like hydrofluoric acid, apply a voltage for a certain period of time, and you can take an orthopedic screw and create nano textures. So very well-defined process. It does not change the chemistry. It only changes the roughness. We, as I mentioned before, we use this anodized screw as an amputee model for a rat. And what we saw was after just 3 days, that nano-textured anodized screw, you can see it right here, enabled the rat to walk after just 3 days. A non-anodized amputee device, the rat was not able to walk for the duration of 28-day study. So when looking at the exit wound, you can clearly see why this occurred. Here's the non-nano-textured conventional amputee device, the screw sticking out of the remaining limb of the rat, the wound is open. So you clearly have a site for infection, inflammation. When anodizing those screws, skin grew, closed the wound, it formed bone formation and enabled that rat to walk. So what's wonderful is the company that is commercializing these, they're commercializing these for the spine. So this is a human x-ray with pedicle screws, they're called, that are used in the spine. If you have a spinal fracture or problems with a collapsed disc, you might receive these. To date, there's been over 14,000 of these implanted that have nano textures, no cases of failure. So this is a much better success rate, obviously, than conventional non-nano textured screws. The second example I want to give is silicon nitride, which, yes.
We are on time.
Okay.
Yes, we are on time.
Let me just finish these last two examples in about 30 seconds. So
Okay.
here's nanotextured silicon nitride, and compared to plain silicon nitride that a company called Syntex is commercializing. They also have seen excellent animal data, no signs of infection when using nanotextured, improved bone growth. They are also commercializing these for the spine. Over 4,000 have been implanted in humans, and again, 0 cases of failure. The last example is a company called Tiber. They are coating titanium using electrophoretic deposition with nanoparticles of hydroxyapatite. They're seeing reduced, we are seeing reduced Staphylococcus aureus colonization, the more rough that surface is, decreased Pseudomonas aeruginosa, decreased ampicillin-resistant E. coli, and they are commercializing these as foot screws for diabetics. Over 15,000 have been implanted in humans, and again, 0 cases of failure. So I hope in this presentation I gave you a pretty good idea of what we are doing in this area of nanotechnology to improve implants, and really share with you that these are in humans. So we are beyond in vitro experiments, beyond animal studies, and really helping real human health with nanotechnology. As a closing, let me just give a plug for this new journal we started, the Research Journal in Medical Sciences. If you're interested in applying for an award or nominating somebody, please send me information. Please go to the journal website and look up our open access free papers. And let me give a plug for a conference that we are running June 12th to 13th in Kenya to talk about health disparities. As we all know, COVID has highlighted a number of global health disparities. And as scientists, we really need to equal the playing field so that everybody has access to high quality health. Thank you very much for your attention. And again, questions, you can always email me, collaborate, happy to collaborate. And thank you for your time today. Thank you.
Thank you very much, Thomas. It was a really very nice, interesting talk about nanotechnology and high impact transfers of technology. And so we are on time, and you are invited to send an email and ask Thomas if you have some question. Now we have 10 minutes of break, and we are coming back at 11:40 if you are free. So 10 minutes of break, coffee break. Well, we are coming back. And now I invite to Waheed Gul, National University of Technology, Pakistan. He will talk about application of advanced nanoparticle for enhancing the physical and mechanical properties of medium density fiber bond. So if Dr. Waheed Gul is there, I think that he's ready.
Hello.
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 You're welcome.
My screen is already shared, right?
Yes, it is there. We can see.
Okay, should I start?
Yes, you can start, yes.
Okay. Welcome all of you today. I'm very thankful to you for your kind presence. I'm also very thankful to the conference organizer for conducting such informative and useful conference. The title of my paper, which I'm going to present, is the application of advanced nanoparticles for enhancing the physical and mechanical properties of medium density fiber board. So let's start with an introduction. What is medium density fiber board? Medium density fiber board is basically a wood sheet pressed under heated and pressurized conditions, and by the application of urea formaldehyde resin, which act as a binder. The density of medium density fiber board is normally range from 720 to 740 kg per cubic meter, while the thickness of this product is normally range from 3.5 to 32 millimeter. Also, there are other products of the same category which are called low density fiber board and high density fiber board with density 500 and 800 kilogram per cubic meter respectively. Basically, medium density fiber board is a composite material which consists of reinforcement and mattress. Here, in medium density fiber board, the reinforcement material are natural fiber, while the mattress is urea formaldehyde resin. Now come to the manufacturing process of medium density fiber board. The manufacturing process of medium density fiber board consists of debarking, chipping, digesting, refining, drying, pre-press, pressing, sanding, and board treatment section. In the very beginning stage, the wood logs are debarked through a debarker machine, and then it is passes to a chipper machine which convert these logs into chips. These chips are passes through a screen in which medium size of the chips are selected for the further digester. Digester is just like a pressure cooker in which, with the help of the steam pressure, normally from 6 to 8 bar, these wood chips are become soft, and a refiner, which consists of rotary and stationary segments, convert these soft chips into fibers. A blow line is injected which supply the urea formaldehyde resin which act as a binder. Now this mixed fiber is passing through a dryer in which these fiber have reduces their moisture content, and the final moisture of the fiber remain from 9 to 10%. These fiber are then passes through the pendester for pre-pressing and mat formation. The mat is then processed to the hot press section where the final manufacturing of this sheet is performed. After the final pressing, the final manufacturing of this board, it passes to the saw in which the extra edges are removed. And finally, the board is cooled in a section which is called board treatment sections. So this was the whole manufacturing process of the medium density fiber board. Now come to the advantage and disadvantages of medium density fiber board. Advantages of the medium density fiber board are: it is economic, it is cheaper as compared to the natural wood, it saves the trees and recycling process. MDF have also fine surface, and they are mostly used for the furniture industry. Uh, Disadvantages: it may be weaker as compared to the natural wood, but it can be used as an interior for interior purposes. Some physical and mechanical properties of this sheet have density, thickness, swelling, moisture content. These are physical properties, while other property like internal bonding, modulus of elasticity, modulus of rupture, screw holding, these are the mechanical property which can be described in the last slides, in the last few slides. These are the applications which can be used in furniture, cabinetry, vapor repulsion, soundproofing, roofing, interior cladding, etc. Now, literature review related to this modified product, medium density fiber board. Few authors have injected nanoparticles in the urea formaldehyde resin in order to enhance its physical and mechanical properties. All the previous work are tabulated in table 2.1, in which several types of nanoparticles were embedded, and based on these nano filler, internal bonding, modulus of elasticity, modulus of rupture, density, thickness, swelling, water absorption, etc., these properties were determined. However, my research work is slightly different. There is a research gap in current days also observed. What is the research gap? The research gap is the physical and mechanical property after the addition of nanoparticles should be improved or equal to the property of a standard nano composite or medium density fiber board. Also, the heat transfer rate and thermal conductivity of the nanofluid should be highly improved. The third research gap is the curing time of the resin and hot press need to be improved, while the most important is the emission of free formaldehyde resin should be controlled while the addition of nanoparticle with natural fiber. The next slide is what are the challenges with this research work. The challenges are low internal bonding were observed, long press time were observed, poor physical and mechanical properties were observed, low heat transfer were observed, and the challenging aspect is also chemical treatment of the nanofluid, which are used as a nanofiller in this research. Aim of this research work that we will develop a medium density fiber board containing aluminum oxide, iron oxide, graphene and reduced oxide, multi-var carbon nanotube and zinc oxide as nanofiller in urea formaldehyde resin. Also, we will investigate the nanofluid after the sonication for distribution and matrix. We will also evaluate the microstructure configuration after the addition of alumina, iron oxide, graphene, reduced graphene, multi-val carbon nanotube, and zinc oxide in matrix. We will examine the physical and mechanical properties of the nanocomposite with the reference composite material. These are my objective: study of interface between nanofluid matrix and reinforcement investigation or investigate contribution of alumina, iron oxide, graphene, reduced graphene, multi-val carbon for improvement the physical and mechanical properties of the nanocomposite. We will also explore the heat and mass transfer mechanism of the nanocomposite and final characterization of the sample manufactured with the reference composite. We would directly go to the raw materials. The raw materials are basically the urea formaldehyde resin and natural wood fibers. First of all, we will discuss the natural fiber. Here, popular stainless fiber were provided by Seal Woodworks Private Limited, Peshawar, Pakistan, an industry of producing the medium density fiber board in conventional method. The average length of the fiber were determined 0.5 millimeter, and the moisture content after passing the dryer were observed 9%. Similarly, SIO analysis were performed, and it was observed that normally the fiber length 0.55 mm were the maximum one. The other raw material is the urea formaldehyde resin, which were supplied by the One Noble Chemical Companies in Pakistan with the following parameter or specification. Viscosity is 230 to 260 centipoise, density 1.22 gram per cubic centimeter, pH value was observed 9, free formaldehyde emission 0.75%, gel time 53, and solid content were 50%. Alumina nanoparticle. This nanoparticle were embedded in the urea formaldehyde resin. So the alumina nanoparticle are aluminum oxide nanoparticle, which I use as a nanofiller for manufacturing of medium density fiber board. Why I choose this nanoparticle? Because alumina has few interesting properties, like it has high hardness, high stability, high insulation, and transparency. The next raw material is zinc oxide, which I also embedded in the urea formaldehyde resin. The motto for the selection of zinc oxide nanoparticle that it has significant anti-antiseptic activity at exact small absorption. It has large surface to volume ratio, and it has exceptional chemical properties. The size of this nanoparticle range from 17 to 19 nanometer. The third nanoparticle which I have choose is iron oxide. Iron oxide nanoparticle, the motive behind this particle, the selection of this particle is due to the antibacterial effect, high particular surface area, anti-cancer, and magnetic behavior of these particles. The fourth one I have choose multi-wall carbon nanotubes. These carbon nanotubes were selected because they have a high tensile strength, high thermal conductivity, and it has the ability to penetrate deeply in the wood fibers. The last nanoparticle which I selected graphene and reduced graphene oxide, because it has thinnest and lightest material known today. The smart material which are used today, it has few attractive property, including high mechanical strength, strong electrical conductivity, high thermal conductivity, and high surface area. So these raw material were embedded in the urea formaldehyde resin for the preparation of nano fillers. Processing were performed with ultrasonic sonications, and after that sonication, sample were prepared of the nano filler, which were tested in the material characterization labs for scanning electron microscopy. So the first scanning electron microscopy of alumina nanofiller were observed. Alumina nano powder and alumina nano filler were tested. Similarly, XRD pattern of the various nanoparticles and nanofiller were also investigated. In the third step, the scanning electron microscopy of the other material like iron oxide were also observed. Similarly, next step, these are the processing of the nanofluids. Nanofluids were prepared as shown in the composition in table 2. These nanoparticles are pure aluminum added in urea formaldehyde resin with different concentrations. And after this concentration, sonication was performed. After the sonication, it was uh, heated and uh, a gel shape or solid shape were achieved. After this gel shape or solid shape achievement, we have tested all the material characterization property like XRD scanning electron microscopy, DSC in few cases, or TGA and DMA analysis. Finally, the nano composite were preferred for each individual nanofillers like iron oxide, urea-formaldehyde, multi-wall carbon nanotubes, uh, graphene oxide and reduced graphene oxide, zinc oxide, etc. Now come to the characterization steps. The characterization were performed by using the following equipment: gold sputtering machine, scanning electron microscopy, XRD, FTIR, density meter, DEC, TGA analysis, universal testing machine, screw holding machine, etc. DMA, dynamic mechanical analysis, and thermal conductivity apparatus were also used to find out its thermal conductivity. The mechanical testings were performed using 3-point bending test using UTM machine with these formula for modulus of elasticity, modulus of ruptures, internal bonding. These are all the mechanical property which can be attained using universal testing machines. Similarly, other physical properties like density, moisture content, water absorption, and thickness swelling were also attained for this unique product. Results and discussion. Now come to the result and discussion section. Scanning electron microscopy of alumina nanoparticle. The selected alumina nanoparticles were observed for scanning electron microscopy, and it was investigated that almost all the nanoparticles have spherical shape, and the sizes of the particle ranges from 80 to 200 nanometer. This result were very close to the previous reported by Peyong Wong, as reported in reference 52. Similarly, the XRD analysis of alumina nanoparticle were also observed, and the peaks were observed at 35, 43, 57 angles. These results were also quite similar with Morley as reference in 53. Scanning electron microscopy of alumina nanoparticle and alumina nanofiller were also observed. If you can see in figure A and B, partial pits are present in urea formaldehyde resin structure, which can be filled by the addition of the alumina nanoparticles. Similarly, EDS analysis of the urea formaldehyde resin with fewer urea formaldehyde resin and with the addition of alumina nanoparticle were also observed. Now we have also observed the bonding of the nanofiller containing alumina nanoparticles. Different peaks were obtained, like peak 3310, which indicate to the free amino group. Similarly, the seen stitching vibration group were observed at 1380. Other bonding OH stitching were observed at 2957.83. Stitching vibration of ALO-AL bond, this is very important, which indicate the addition of alumina nanoparticles in the urea formaldehyde structure. Similarly, the XRD analysis of the various concentration of the alumina nanoparticle in the urea formaldehyde resin were also observed, and it has been found that by default or naturally the urea formaldehyde resin has no such peak. When we added the nanoparticles, its structure cannot be changed. However, at angle 61.25 and angle 66.5, small peaks were observed due to the addition of these nanoparticles. So almost structure remains same while we added the nanoparticles in the urea formaldehyde resin. So it is amorphous in nature. DEC analysis of were also investigated. So the total heat content increases with the concentration of alumina nanoparticle at 120 degree centigrade. For 1.5% of the alumina nanoparticle, there observed to be the formation of the bond in the urea formaldehyde resin. The next observation is the TGA analysis. From the graph, it is indicated that as the temperature rises from 20 degrees centigrade to 140 degrees centigrade, so minor change in the weight loss has been observed due to the moisture absorption and dehydration occur. This was also investigated, or similar results were also investigated by the French, as reported in reference 59. So due to the hydration of the urea formaldehyde resin, considerable weight loss occur, which indicate the presence of intra and intermolecular carbon and hydrogen bond presence. Similarly, nanobus MDF were finally performed. So if you can see the scanning electron microscopy of the final nano MDF, it has been observed that at 0% alumina nanoparticle, partial pits were widely were visible in the structure. But when we added the alumina nanoparticles in the urea formaldehyde resin for the manufacturing of final board, there is no such open or partial pits. So it indicates that the gaps which are present in the conventional method made MDF are completely covered by the addition of the alumina nanoparticles. These are the few results of the mechanical property, internal bonding, modulus of elasticity, modulus of rupture, densities with different concentration of alumina nanoparticles. 0% alumina means that we have not added any alumina and we made the MDF in conventional method. 1.5, 3% and 4.5% concentration were added in the urea formaldehyde resin, and the results were quite comparable with the reference one. So it has been observed that while the addition of 4.5% alumina nanoparticle, the internal bonding value is normally 0.76 Newton per millimeter square, which is the highest value, and the standard value for this product is 0.7. Similarly, the modulus of elasticity and modulus of rupture property also increase. The density also increased due to incorporation of these nanoparticles. Other analysis, statistical analysis were also observed for the sample characterizations and result verification and accuracy. So ANOVA analysis were also carried out to find out the accurate results that actually the improvement occur in the physical and mechanical properties. So these are the final table of the properties: internal bonding, modulus of plasticity, modulus of rupture. With 0% alumina nanoparticle, 0.161 internal bonding were achieved. At 1.5% concentration, 0.67 Newton per millimeter square internal bonding value were achieved. At 3% concentration, 0.68, and at 4.5% alumina nanoparticles, the value were quite high. The next nanoparticle is the zinc oxide nanoparticles, which has 4 levels: 0%, 1%, 2%, and 3%. These percent value were added in the urea formaldehyde resin for the manufacturing of nano MDF. The summary of this whole edition of the zinc oxide nanoparticle, that the physical properties were significantly improved, but the mechanical properties were not improved. So it means that by the addition of zinc oxide nanoparticle, it enhanced only the physical property like thickness filling and water absorption by 38 and 12% respectively. These are the manufacturing process, which no need to describe here. These are the scanning electron microscopy of the zinc oxide nano, which are flower in shapes. The XRD result of the zinc oxide nanoparticles. The highest peak were observed at 36 angle, which is quite similar with the Raman-Dog references in 62. The scanning electron microscopy of the zinc oxide uraformaldehyde nanoresin were also observed, and the white particles indicate that these are the zinc oxide nanoparticle added in the urea formaldehyde resin. Similarly, differential scanning calorimetry of the urea formaldehyde zinc oxide nanofiller were also investigated, and at a peak of containing 3% of zinc oxide nanoparticle at 100 degrees centigrade, you have observed the highest peak at 3% zinc oxide in urea formaldehyde resin. Similarly, the thermogravimetric analysis, TGA analysis, is also investigated for the zinc oxide nanofiller, and at a temperature which rises from 25 to 160 degrees centigrade, vaporization occurs and the weight loss is minor. The similar report were also observed by Romley in reference 70. So the water absorption properties and thickness swelling property is already indicated that zinc oxide only improves the physical property, that is thickness swelling and water absorption, and do not improve the mechanical property strongly. The third nanoparticle is the multi-wall carbon nanotubes, which the whole summary of this addition of this nanoparticle, that at 0%, 1.5%, 3%, and 5% concentration of the weight, the nano MDF were manufactured. It has been observed that the physical and mechanical properties were improved by 21.15%, 30%, 28%, 44%, and 29% respectively. The next step is the functionalization of multi-wall carbon nanotubes. While adding the nanoparticle multi-wall carbon nanotubes is a challenging task because it agglomerates with the urea formaldehyde resin. So first of all, you have to functionalize multi-wall carbon nanotubes. Acid treatment were performed in order to properly solve these nanoparticles in the urea formaldehyde resin, and functionalization group like hydroxyl group and carboxyl group were performed at the stretch of 3,200 and 3,450 per centimeter were observed. Similarly, at carboxyl group stretch at 1450 per centimeter were functionalized. So after functionalizations, we can use it as a nanofiller and completely mix in the resin. These are the scanning electron microscopy of the simple urea formaldehyde resin and the addition of multi-wall carbon nanotubes. The particles are visible, multi-wall carbon nanotubes are visible, and these particles also cover the partial pits in the figure A by the addition of these nanoparticle. Differential scanning calorimetry of multi-wall carbon nanotube. Differential scanning calorimetry of the multi-wall carbon
We are on
nanotube.
time.
Sorry?
We are on time.
Okay. So let me finish. The fourth one is the graphene and reduced graphene oxide were also added. And I would like to compare all these nanoparticle addition with the urea formaldehyde resin. So these are the final properties. Water absorptions here in this case, the graphene and reduced graphene oxide has the highest or the better properties as compared to the other nanoparticles and the reference nanocomposites. modulus of elasticity is pretty high for in case of the multi-wall carbon nanotubes. So these are my conclusion. The heat content value was increased based on DMA analysis. The storage modulus of elasticity was increased. Scanning electron microscopy of nanofiller and finite MDF revealed the parshapet were covered by these nanoparticles. XRD indicate that amorphous nature was not disturbed by the addition of nanoparticles. And the final, that the thermal stability, thermal conductivity, and heat transfer rate were increased due to the addition of these nanoparticles. The most important is the emission of free formaldehyde was controlled by the addition of these nanoparticles. The thickness filling and water absorption property were also improved. The mechanical property like internal bonding, modulus of rupture, and modulus of elasticity were improved at a standard level. And the hard pressing time was also decreased, which increased the productivity of this product. So these are the references, and any questions are welcome. Thank you very much for your attention and listening.
Thank you very much for your presentation, Wahid, Gul. If there are some questions, we don't have so much time, but in the case that there are many, you can contact him via email. So if there are not questions, we proceed with the next presentation. Thank you, Wahid. If you can
thank you very much, sir.
Come share the screen. We thank you. So the next speak is, we have the pleasure to invite Negi Habit from Imperial College of London, UK, to deliver the keynote speech on a small activating RNA from concept to phase 2 clinical trials. Unfortunately, she cannot be there virtually, but we will show her presentation right now. A few seconds, we will share. Okay, we are there. We are having some little problem with the sound. We will try again. Sorry about this. Well, we have a problem with the presentation recorded, but for this reason, we'll continue with the next one. Now, we invite to talk to Jose Michael Leonida. So we have a modification in the agenda as well. So I call up Michaela Leonida, Firelight Dickinson University, United States, to deliver her talk on tannic acids as modulator of nisin release from composite with antibacterial activity. Michaela Leonida, she's there, I think. You are welcome to share the screen.
Hello, do you hear me?
Yes,
okay.
We can. Thank you.
So, thank you for being here and hopefully listening to me. I'll talk about our study of tannic acid as modulator of nisin release from composites with antibacterial activity. It is a joint study between our chemistry department, the Department of Biology at our university, and l'Institut Chimie et Matériaux de l'Université de Paris. So also it has 3 undergraduate students who worked on it, which is maybe less common or more encouraging for all of us. So it is the study started when after a day like today, somebody contacted us and told us about their problem. So it was a huge food company who had problems with this peptide nisin, which is used as a preservative in foods, in meats. And the problem with it, it's good, but it leaks in lipophilic environments. So and we were tasked to we proposed to encapsulate it. So what is nisin is a bacteriocin which is secreted by some bacteria, in this case Lactococcus lactis, which is a gram-positive bacterium, and their role is to protect those bacteria by similar types of bacteria. It's a small, relatively small peptide. You see it in the picture, and it's used as preservative in foods because it's categorized as GRAS, so generally regarded as safe by the Food and Drug Administration. So besides the drawback I mentioned, or in spite of it, recently it attracts more and more attention, and it started to be of interest for the cosmetic industry. Also, our school is among the 2 schools in the United States which has a section offers a degree in cosmetic chemistry. And in our lab, we had and still have experience in encapsulation in chitosan, nano-sized chitosan matrices. We like this biopolymer because it is inexpensive. It's obtained most of the time chemically from the deacetylation of chitin. And lately, more and more small companies offer it obtained by fermentation from fungi. Also, it is of interest because it is active against both gram-positive and gram-negative bacteria, and it has a modest antioxidant and antifungal activity. Also, for the purpose of encapsulation, the fact that so it is basically polyaminoglucose with some more or less N-acetyl groups, which so due to its structure, it has the ability to cross-link, and in our case, we chose to cross-link it with the sodium tripolyphosphate, which has a modest antibacterial activity itself. And the target of our study, I mentioned to be used as preservatives in foods and cosmetics. Because the study started as trying to solve the problem of niacin leakage, besides besides providing for ourselves niacin and chitosan, we also added to the cast tannic acid, which from literature, it is known that it's very powerful antioxidant. So speaking from the cosmetic industry point of view, it's interesting for protection against free radical, protection against skin cancer, and premature aging. So due to its many phenol groups, so it makes complexes with proteins, and we thought to try to see targeting not just the protein complexing, but also possible synergistic effects in the antimicrobial and or antioxidant region. So the ionotropic gelation between chitosan and tripolyphosphate is a green process. So it's highlighted here. This solution, it only dissolves chitosan in acetic acid, ultrasonication. And then we prepared several sets of complex particles. So just nanochitosan for comparison purposes, and then particles with different concentrations of niacin, and two sets of particles having as cargoes both niacin and tannic acid in different ratios. So we had previously experience encapsulating proteins in nanochitosan matrices. So in this study, we had reported the encapsulation of two proteins, respectively. One of them, the diaminoxidase, otherwise known as histaminase, is interesting for towards treatment of allergies, and catalase, which is the strongest natural antioxidant known. The problem is, so we had experience, but those proteins are much bigger compared to the 3,000 plus daltons of niacin. Those are 140, the diaminoxidase, and catalase 240 kilodaltons. So this would be the synthetic mixtures, as you can see, there are two sets of, so besides the different Nicene loads, there are two sets having both the Nicene and tannic acid. After preparing them, so we characterized the particles, the composites. One method was using FTIR, and there are A and B show two, they show proof of both cross-linking and encapsulation. The two peaks at 1637 and 1543 reciprocal centimeters are a proof of cross-linking with tripolyphosphate, as are the peaks above 1200 for the P double bond O stretching, and those at 887 and 891 reciprocal centimeters for phosphorus oxygen binding. And also presence of the cargos is provided by the enhancement in hydrogen bonding and the broadening of the band starting at 3300 and extended towards 2900, almost obscuring it. It's more difficult to see the TAE, the tannic acid peaks, because they because of the difference in relative amounts, and also due to the masking by the other components. But its presence in the composites has been proven by other methods. So the table here shows three other items used to show, to evaluate encapsulation. So amino groups, and we see how it was calculated, the same as the encapsulation efficiency and the loading capacity. So probably it's more useful to look at the conclusion. The table is not very reader friendly. The ratio of the residual amino groups is interesting from 2 points of view: to evaluate cross-linking, and also as a predictor of potential antibacterial activity. And so comparing the numbers, so addition of Nicene compared to the nanochitosan, presence of Nicene decreased a little the number of residual amino groups, which was expected due to additional cross-linking. And the presence of the tannic acid accentuated this trend. So we see here in the presence of Nicene only 46%, 10-to-1 Nicene to tannic acid 38, and 35 at the higher tannic acid content. So the dependence in the case of so the variation proves cross-linking, and for the encapsulation efficiency, so the numbers increase with the increase of Nicene concentration, which was reported by the encapsulation of other proteins. And in the presence of tannic acid, due to more complexation and more cross-linking, the values are a little lower, but observe the same trend with increasing concentration. The same trend is noticed when in the particles containing tannic acid in regards of the tannic acid encapsulation. For the loading capacity, in both cases, it increases with increasing concentration of that particulate component. The same trends were observed by us for the other two proteins I mentioned, but the values in encapsulation efficiency and loading capacity were higher. So we ascribe this difference to the difference in size between the proteins and the higher lipophilicity of lysine compared to the other two. When measuring the size, we had a surprise to see that compared to our previous experience, these particles showed massive aggregation. And the aggregation, the sizes decreased in when cross-linking density increased, so decreased when lysine was present compared to nanokitosan, and even more compared when tannic acid was present compared to only lysine. The positive zeta potential values tell us two things. The fact that all values are positive, so validate the ratio of residual amino groups, but also since all of them are lower than 30 millivolts, they confirm the tendency to make agglomerates displayed by sizes. So I was mentioning our experience with the bigger proteins of therapeutic interest. So the difference is that the behavior is different. If we look at the numbers, much less aggregation is present. The same positive zeta potential is displayed, and we ascribe the differences, as I was mentioning, to not just to size and lipophilicity, but also to a different mechanism of making the particles. While lysine at the pH of 5.5, the particles were made, it is positively charged, so it becomes a competitor to the positively charged chitosan for the negative charges on the tripolyphosphate. At a pH of 5, those shown in the slide particles were made. Both those proteins were negatively charged, so interacting with competing for chitosan. So the protein polysaccharide proves to be a more important factor in this type of composites. We used heavy ultrasonication. If you notice in the synthetic procedure, but we didn't try to use it more after adding the cargos, because our previous experience encapsulating lipophilic molecules of antibacterial interest told us that additional ultrasonication wouldn't make a difference in size or zeta potential. So another method used to characterize the composites was scanning electron microscopy, and it proves again the formation of aggregates without displaying significant differences between the chitosan-based particles, those loaded with lysine only, or the lysine and tannic acid containing composites. The only morphological slight difference may be seen as the increase in smoothness of the particles when lysine was added, and even and the trend continuing with increase in tannic acid added. Talking about comparison, so these would be some samples of the two previously reported proteins, which again, in spite of the difference in protein, difference in sizes, and between A and B are done using chitosan 75% deacetylated, like the one used in reported lysine particles, while so those would be B and C, while D and E are nanoparticles enclosing respectively the two reported proteins, histaminase and catalase, in chitosan made from fermentation of fungi of much smaller molecular size and 96% deacetylation. So no morphologic differences, difference in higher encapsulation efficiency in the more deacetylated ones. The same lack of difference we had noticed previously in nanochitosan matrices encapsulating antimicrobial metallic species, copper and silver, respectively. So to evaluate the role, the potential modulating role in tannic acid, we so in the in the graph on the A, so we see the different composites. The more telling, I would say, is B, which shows that so the release was measured in buffer at a pH of 5, comparable with since we were targeting skin applications in cosmetics. So we use this pH. We see, yes, lysine, we solve the problem with fast release, but lysine only, it's a non-practical level, while addition of tannic acid, so increase the release sensibly, more so when there is higher content. So comparing it with our previous experiences, what I want to mention is that Like in the case of niacin and tannic acid, increased release is shown when concentration increases. And I display those because the difference is the bigger sized proteins and more hydrophilic showed increased release over the same period. Our target, as I mentioned, were applications for the skin as preservative, antioxidant against photoaging for skin formulations. So we prepared in our lab an oil and water emulsion, water in oil, and we purchased simulated human sebum. So formulations with different lipophilicity to study the same release. So we formulated our particles into respectively into those three different preparations, and the best behavior we noticed for the least lipophilic one. So the oil in water with a content of about 11% fat. So for all of them, we obtain a sustained release. We don't see the burst we saw in buffer, and which we had ascribed to the niacin adsorbed on the surface of the particles. We observe the release in lipophilic environment being beneficial, less this abrupt increase, which would be correlated with the decrease, the matrix degradation after a number of days, which here is present only in this compound with very high lipophilic content. And also we see that the lipophilicity of the environment brought the release, not only kept it sustained, but brought it at a more practical level. So because of the presence of tannic acid and because chitosan is a modest antioxidant itself, we assayed our particles for antioxidant activity. So, and compared it with, you see at the bottom of the table, the components. So we had a surprise here. While the Nanoscience provided enhancement, we see here the nanochitosan particles compared to chitosan is a huge increase. The effect adding niacin didn't provide any synergy. Yes, increasing it increases the antioxidant effect, but not as much as we expected. The surprise was the presence of tannic acid, which is helpful, but definitely, and again, it increases with increased content, but definitely not showing the synergy we hoped for. Now I have to mention that the comparison may not be fair because when tannic acid and niacin were assayed separately, the concentrations are much higher than those present in the particles. And also there is the problem of the added diffusion to come out of the particles. So my students who are going to get a degree in a master's in cosmetic chemistry wanted to try the sunscreen protection capability of our particles. We only tried it on two of the particles containing both niacin and tannic acid, and we used the Mansur method. If anybody is interested, I can provide the reference. So
Excuse
the
me.
results were not.
We are on time.
I'll be done very soon. So the
Okay.
results were not extremely interesting. Higher tannic acid provided 5.6 protection factor, which is mentionable. The less tannic acid, less so. I'll be short on the last characterization, the antibacterial effect. So all of them, to make it really short, so we assayed our particles and the components separately, and also the added components, so to evaluate the effect of the nano size. And the results were good, meaning that all the nano size proved beneficial by a decrease in both in effect against the gram positives, but against the gram negative species, both species, E. coli and Pseudomonas aeruginosa. They are of interest, as is Staphylococcus, for both the food industry, pharmaceutical, and cosmetic industry. What is tremendously interesting is the synergy, not only against the gram positives. If you remember, both niacin and chitosan are active, but the biggest synergistic effects were obtained against the both gram negative species, especially E. coli, while it is a known fact that niacin is not active itself against the gram negative species. So the last is our campus, and I promised my students that I'll show their pictures. So they worked on this project. Thank you for listening.
Thank you very much for your talk. It was a very nice talk and very interesting. So time for the question. We don't have time really. We are really
If anybody is interested, my email is listed on the conference website, and I will be happy to connect and exchange information. Thank you again for your attention.
Perfect. Thank you very much for this information. And now continue with the scientific speaker session. I call up Mohsen from MES Lightweight Design Engineer in Egypt to deliver her talk on nanotechnology uses nowadays. Are you there, Mina Hassan?
Yes, I'm here. Thank you.
You're welcome. You can begin, share your screen.
Okay. Can you see my screen now?
Yes, we can. We hear you well.
Okay. Okay, hello everyone. I'm Nanoscience, Senior EMS Layout Design Engineer at SR Vision. I'm gonna talk about nanotechnology usage nowadays. So all of us today are using or having or dealing with nanotechnology daily in our routine, from using mobile phones, PCs, laptops, and even our kind of wearable devices. Lots of us actually are using now wearable devices. So I'm going to concentrate and focus in this presentation in wearable devices. Then we'll go deeply inside the wearable devices by introducing the biosensors and bioimpedance and how to measure it. Then we will need to have a brief introduction to the nanoelectronics, following by Bluetooth Low Energy and optimization algorithm. And then I will relate all of those topics together to tell you the main idea of having a circuit-based biosensors. Then I'll go through little examples such as handheld biosensors and artificial human eardrum. So as I said before, that all of us are dealing with, or most of us are dealing with wearable devices at our daily routine, from hearable devices, smartwatches, and etc. So lots of websites and actually papers have done and statistics last year for the wearable devices, and they found that there were top 5 wearable devices used from the worldwide last year, and top 1 goes actually for smart hearable, and followed by smartwatches, smart patches, smart clothing, and then or top 5 goes to smart implantable. That means that the wearable devices market size is growing up year by year. So according to Precedence research, they found that the size of the market size of the wearable devices at 2021, it was $121.7 billion, and they expect it will surpass around $392.4 billion by 2030, with a growth rate 13.89, which means that wearable devices is actually a very huge market size. So let's go deeply inside the wearable devices. So let's talk about that. Most of wearable devices actually contain biosensors. So how biosensor can measure or test any biological tissues. So the main idea from measuring bioimpedance is by applying an excitation on the biological tissue and then measure the output from the biological tissue. And we have actually 2 modes from this methodology. We can apply voltage and measure current, and then we can also apply current and measure voltage, which means that the biological tissue actually can act as resistors and capacitance. So they found that the biological tissue actually depends on the type of the tissue, cellular membranes, extracellular membranes, and etc. And they found actually that it has 2 performance according to the excitation. At high frequency, they found that the excitation can go through the biological tissue, and at low frequencies, it can go in between the biological tissue. So we can say that any biological tissue actually can be mimicked or can be modeled using electrical components from capacitors and resistors. But we found that the most elements that can well describe the nature behavior of any biological tissue is the fractional element. So what is fractional element? Let's go briefly or have a brief introduction about the fractional element. As we know, or most of us know, that we have integer capacitor and integer inductor, which its impedance is 1 over SC and SL. So what about if we have this order, not an integer order, if it has it becomes a fractional order? So that's give us lots of performance to the capacitor and the inductor. And those are the applications for the fractional order, derivative, and integration. So let's have a quick example from sine and cosine. We know that we have sine and cosine in its order case, in its integer order case. So if we how can we mimic or have an analogy for the signals between sine and cosine that can be well described by the fractional integration? So that's actually the best thing we can describe the nature of behavior, as it is not, as a nature of behavior actually is very complicated, and we cannot describe it using straightforward or integer elements. We need fractional orders to can describe all the behavior of the nature of behavior. So back to the bioimpedance or the biosensors, we have lots of devices. We have actually two types. We have bench devices and wearable devices or portable devices. Bench devices actually are very large and high cost, but wearable devices actually solve those problems. As you can see here, we have here an example for SP150, that's bench devices, and also here for portable devices. That's a system on a chip or hand-held portable devices, which can actually sense the ECG signal from a human. And it actually can be modeled, the signal, the output can be modeled using cool model, which well describe actually, this model can well describe any biological tissue. And also this one, which represent a circuit based, depends on an oscillator, which can also test and measure any bioimpedance or any biological tissue. In this presentation, we will focus on this one, or this type of devices. So we have lots of challenges in biosensors, such as selectivity and sensitivity for accurate detection, and limitations in detection of mutated forms of viruses, also the high time or low speed, and the cost consuming for diagnosis, and the high power consumption and large area. So we need something to can solve this limitations and challenges. That's what the nanoelectronics actually promises and can solve those challenges. So lots of foundries actually have introduced small technology nodes where can solve the high speed, power consumption, the area, and the accuracy. And they actually moved from the planar transistor to another definition, such as FinFET, gate-all-around, and MC-FET, which actually lead us to have lots of transistors on one chip, which actually managed us to have system on a chip and with the very small wearable and hand-held devices. And one of the modules which could be actually embedded on this system is Bluetooth, which is very important, and actually it has occurred in all or most of the wearable devices where it has a transient and a global wireless communication between two different devices. And it actually has lots of applications, and one of that is the wearable devices. Okay, as we said before, that we have a very complicated system now to can actually measure the bioimpedance of any biological tissue. So we need an algorithm to can solve this complicated function and this complicated problem. So the classical optimization algorithms couldn't actually solve this problems. So we will shift, or we will use meta-heuristic optimization algorithms such as FPA and any kind of meta-heuristic optimization algorithms. I have used actually in this in our designs FPA. Okay, so what is meta-heuristic optimization algorithm? It is actually an algorithm that can find and get the best element of from some set of available alternatives at a dedicated area. So let's relate all of those topics together. So as we said that we have a portable device now, which has actually system on chip, which contain our biosensor and more modules such as Bluetooth. And actually it will sense the biological tissue. As you can see here, we can use any biological tissue. And as we said, how the biosensor actually can sense any biological tissue, it actually, we apply an excitation on the biological tissue, then we will measure its output, and using any kind of meta-heuristic optimization algorithms, then we will have parameters which model this biological tissue. As we said, cool model is the best model to can model any biological tissue. So as we said, we will apply an excitation, measure, optimize, and extract the parameters. And those actually, we have designed around 5 devices which can measure the biological tissue, any biological tissue, with different topologies. But here I'm gonna only take one device to show you. So here we have used actually this circuit, which depends on a relaxation oscillator, and it's called actually many component relaxation oscillator. And we have this is the original one, and we have replaced this integer capacitor with the core model, which represents a biological tissue. We just did this first to prove that this device will work well when we embed it in a biological tissue. So we did all the steps we said before. We had applied an excitation, then after that we measure the output, then we used meta-heuristic optimization algorithm, and then we got the data of the unknown parameters of the cool model or any biological tissue. And that was the prototype of those devices, and we have compared it actually with a trusted impedance analyzer called SP150. I have showed you at previous slides. And as you can see here, we have the relaxation oscillator or this device output with red line, and the SP150 was the dotted line. And as you can see here, it is actually they are almost the same. We have actually did lots of experiments. You can find that at actually our paper, but here I just gave you an example for 2 fruits. It could be actually applied on any biological tissue, not only fruits and vegetables. We have tested on lots of biological tissues. Okay, so I'm going to talk about another model, which is artificial human eardrum. Actually, we have 3 types of the artificial human eardrum, but I'm going to talk and focus on type 2 only now, as we optimize this this type. Actually, type 2 from artificial human eardrum, it actually used for headphones and hearing aids, also measuring earphones, both sealed and unsealed. And as you can see here, that is the integer model for the artificial human eardrum. And this two branches actually are modeling the human eardrum. So we wanted to minimize it and optimize this complicated circuit. So from the ratings of the artificial human eardrum, we found it looks like a band stop filter. So from here, we got the idea to minimize those two branches. So we actually have used this design, which combined from inductor, fractional inductor actually, resistor, and fractional capacitor. We actually first initiated or started with fractional order elements as it is a generic element. Then we used the meta-heuristic optimization algorithm to get the parameters from those for those unknowns, and we found that the resistor actually has a parameter, a value with 1 giga-ohm, which could be neglected or represented by an open circuit. And the order of the fractional capacitor is actually almost 1. So we can use an integer order of capacitor. But for the inductor, we found that the best value was with a fractional order 0.4. So that is the most complicated one. So we have used actually to design it. So we used actually to design it the transistor level and nanoelectronics. And here we have the advantages for using nanoelectronics and nanotechnology in designing this fractional order inductor. And actually, for more details, you can find how we designed this inductor at our papers. And I will go back here to let you see the result. As you can see here, the result actually for our optimized model are actually near to the results or the readings of the artificial human eardrum. So let's conclude our session. As we said before, that wearable devices and biosensors are so trendy now and has a very big market. So we have to take care of that and invest more in the wearable devices. And it has lots of challenges. So nanoelectronics actually improved the performance and solved most of the challenges in the nanoelectronics. And nanoelectronics actually let us or give us the chance to have lots of systems on the same chip. So we managed to use actually Bluetooth Low Energy and lots of modules on our wearable devices. And also we got that the tissue have a behavior like electrical elements from resistors and capacitors, and also the fractional element is the best element which can mimic or model the nature behavior. And also we found that oscillators and optimization algorithm together can perform a bioimpedance measurement devices. And thank you. And I will be pleased if you have any questions.
Thank you very much for your talk, Mina. The questions are welcome. If there are not questions, you can contact her as well by email or chat. Well, I think that maybe right now there aren't questions, but later maybe yes. We are on time to take a lunch break for 20 minutes. So we are coming back in 20 minutes. So you are all invited to take your time for a lunch. See you later. Well, good afternoon to everyone. We are coming back after lunchtime. We begin another time, and we take this immense pleasure to invite Hamidreza Siampur from University of Cambridge, UK, to deliver talk on hybrid quantum photonics with nanodiamonds and plasmons. So, Hamidreza, you're welcome.
Thank you very much. Can you hear me?
Yes, yes, we can.
Okay, very good. So let me just share my screen. Right, can you see my slide?
Yes, we can.
Okay, very good. All right, good afternoon, everyone. Thank you very much. Thank you, organizer, for setting up this wonderful conference. So my name is Hamidreza Siampur. I worked at University of Cambridge and also a lecturer at Queen's University of Belfast. My research background is mainly concentrated at the interface of quantum optics and nanophotonics. I did my PhD in the field of plasmonic waveguides and the coupling to quantum emitters for chip-based optical applications for making chip component optical devices, quantum optical devices. This followed by two postdocs, one in Sheffield in quantum dots and photonic crystals for chiral quantum applications, and one in Cambridge with NV centers in diamonds for quantum optical sensing. So for today's, I will concentrate on my work in nanodiamonds and plasmons. Maybe I could start with a little bit background, what I did and what interested and what brings me to this field. So I was working like with classical optical components and electronics components, and the kind of aim was to bring these transistors down to single atom level, and we already knew from Moore's law that this has been kind of a continuous trend for 50 kind of years, that every year or every 2 years this kind of density of transistor per chip is going to be doubled. And this at the end actually we reach to quantum levels of atoms, and quantum effects will appear, which might have also challenges, at the same time opportunities. One of the opportunities to make use of so-called quantum superposition entanglement to and introduce new paradigm of computation and information processing by kind of doing parallel computing. So for this, there are a number of platforms already demonstrated and already explored in academic research, and also some of them already commercialized. Probably you already heard about superconducting qubits. Some companies like Google, Microsoft already invested on these platforms. They already make like 50, 60 qubits using this platform, because they have kind of very strong interaction. They can couple to each other, they can talk to each other. At the same time, we have trapped ions in the other side, that they have very good coherence and very good kind of coherence time, which is very also needed for quantum applications. But kind of challenge here is easy to like control single atom, but scale it up like it's gonna be difficult. Make it like 100 different atoms at the same time. It's gonna be different. So in between, we have a number of other platforms in solid state that trying to kind of combine best of both worlds. So having strong interactions like superconducting qubits and also long coherence time like atomic systems. So here we are trying to explore atom-like emitters in solid that we can make monolithic integration with what we already knew from solid state systems, and make components and try to use common modes to be able to interact with emitters and atom-like systems. And here actually we might not be not needed actually to bring these atom-like systems very close to each other, but at the same time we can use modes, common modes like optical modes, for example, to be able to carry information between different nodes. So in this regard, we use photons, which can maintain the coherence for a long time because they do not interact with medium. And exactly for this reason that they do not interact with each other and also with medium, we need to kind of bring expertise from photonics and try to kind of manipulate or kind of design structure that enables us to make photons interact with atoms. So in this regards, one of the main opportunities is to make use of plasmons. These are also photons, but then they can confine a smaller scale. This can enhance your interaction with atom-like systems. And also, it can also make photonic structures miniaturize your optical devices for chip-based applications. So there have been a number of different demonstration in this regards, how they can like bring these plasmonic structure like plasmonic waveguides to the emitters that can be quantum dots, can be, for example, color centers in nanocrystals, like what we are talking about here, for example, nanodiamonds with embedded color centers like NV centers or other group colors, for color centers that they can kind of absorb this excitation light, your pump laser, and then emit light in non-classical regime, emit single photons, and these single photons also can be coupled to this plasmon, and this plasmon now they can confine well beyond the diffraction limit and propagate through the rest of the chip. So what you see here is one of the demonstration we have done. So you see the screen laser, which is our pump laser. We kind of shine this laser through our nanophotonic structures. You have some grating here. This light will kind of transfer to plasmons because here we have metallic structures as a substrate. And then these plasmons propagate through the waveguide. They already excite a plasmonic mode. This plasmonic mode reach your nanodiamonds, your crystalline nanodiamonds. And these nanodiamonds absorb your light. There are some defects already introduced in nanodiamonds that they can absorb light, and then they emit light quite efficiently. So this light is going to be single photons down to level of photons, like non-classical light. And then these single photons at different emission wavelengths, they can also excite modes at their own wavelengths and then couple to the waveguide and propagate through the waveguides now in red light. and then outcoupled from the gratings, from outcoupler gratings. But this is kind of like a structure that we are going to discuss today. So as you already see, these nanodiamonds are the range, the size of these nanodiamonds are in the range of few 10 nanometer. They have been fabricated under high pressure, megapascal, and high temperature, about like 2000 degrees. This is kind of like to mimic the natural condition of diamonds that naturally exist under the ground, like at about 100 kilometers. They have naturally introduced defects like nitrogen vacancy, but we can also introduce our own defect center, our own color centers, like we can introduce germanium or silicon or other tin, for example, into this diamond during the growth, and then they form kind of like atom-like or molecule-like system inside this diamond that are protected, that are very stable. They can absorb your excitation light and emit light quite efficiently. One of the challenge here is to how to kind of bring accurately these nanocrystals very close to your photonic structures, your plasmonic structures, because otherwise it's difficult to couple them to your systems. We have developed a technique to accurately position these nanocrystals inside our chip. These nanodiamonds that are already inside the solution. So we spin coat the solution on top of the substrate that we have here. We have silicon wafer, and then on top there is a layer of metal here, for example, silver. And we have also some markers on top. So as you see, we have some like cross markers here to be able to kind of determine the position of these nanodiamonds. So then we choose a specific part of the chip and then do some typical confocal microscopy. This is kind of a raster scanning of your laser, and then see what come out like from the output. So whenever you have like nanocrystals, they absorb your green laser and then they emit light at the emission wavelengths. And then we see actually what you see here, you already see the markers, the gold markers that we have these crosses. And also you see some dots here. And these dots, we can kind of characterize them to make sure that these are indeed our single photon sources. We can do, for example, anti-bunching measurement. So we bring this light into a beam splitter, and since they are like single photons, they can only turn on one of the detectors at the end of this beam splitter. Then by introducing a correlation between two detectors, we are able to distinguish based on the anti-bunching signature that whether they are single photons or not. So the zero delay time between these two detectors. So you already recognize a dip in your correlation function, which is kind of like a signature that you have indeed single photon emission. So once we recognize that they are single photons, so we can also measure the spectrum of these dots. So as I said, they can absorb your pump laser, your excitation laser, and they emit light at different frequency, different wavelengths regime, depends on the type of this defect center. For example, if they are NV center, they have kind of a broad emission wavelengths from 550 to 8 to 750, for example, and the 0409, which is like the coherent part of the photons that is useful for communication, and the sideband, which is phonon sideband of the emission wavelengths, is useful for sensing. For quantum sensing, we can also use this part as well. But for communication, we are only interested in this 0409, which in NV center is at about 637. Or we might have different defect center, for example, silicon vacancy or germanium vacancy, depends on type of nanodiamonds that we are using, which in this case, this introduced like new type of emitter. Each of them has their own advantages and disadvantages. So once we characterize the emitter and the type of vacancy center, the type of color center, we can go down and get some additional information from the image, from this optical image that has limitation based on diffraction, limit of light. But we would like to position this nanocrystal down to nanoscale, so we can add our additional information about the profile of the emission. For example, if this is like kind of a Gaussian profile, so we might be able to go and find the peak of the emission. And then based on very precise coordinate that we made after this characterization, we are able to fabricate our structure using electron beam lithography. We can make our structure, waveguide, cavity, or interferometer, or whatever structure you are interested in. Since we know the exact position of this nanocrystal, and our electron beam lithography also can easily go down to this nanometer scale resolution and fabricate structure in a way that your emitter now is embedded inside the waveguide mode and can efficiently couple to the structure, to the optical mode. And this is the optical mode that can be used to, for example, make a link between several of those emitters, those structures. So this is an AFM image of the structure that has been fabricated afterwards. We use like HSQ, it's kind of a negative electron beam resist. It can make structures very precisely with very good resolution for nanometer scale optical devices. This HSQ is a polymer that tend to be silicon dioxide after development. So after development, you have this kind of silicon dioxide-like structure on top of metal. This can kind of excite a mode, a plasmonic mode. We call it dielectric loaded plasmonic mode, which can efficiently interact with your emitter. You can excite it, it can boost the emission rate, and it can also couple it to the chip-based components. And in this scenario, you are not also very limited. You are still limited with diffraction, but not as much as you are limited with pure dielectric structures. So we can go down to smaller scale in this new device design. So
recording in progress.
Once we are kind of fabricate the structure to make sure that we are indeed couple the emitter to this waveguide, we can again do the excitation. We can bring this green laser on top of the emitter and then excite it, and then see the single photons that are going through the waveguide and outcouple from the end. We can detect these photons from the outcoupler as well. So this is kind of like
we are on time.
Yeah. How much time we have?
We are on time. 1 minute maybe.
Okay. So maybe to then to conclude, these are the number of structures that now we fabricated based on this technique. We are able to fabricate interferometer, the waveguide, the cavity structure like that. And also we are able to kind of remotely excite these emitters when we introduce single crystalline fleck and single crystalline metal. And to conclude, I would like to kind of compare this structure that we have developed based on this technique with other structures in terms of propagation lengths and also in terms of confinement, which can introduce like the per cell enhancement or emission rate enhancement. So there is already a trade-off between confinement and loss in plasmonic structures, and in our structure we are able to kind of use the best of both worlds, confinement of plasmon and also hybrid photonic plasmonic, to be able to increase the lengths of the propagation. So within this, I would like to thank you all for your attention. Thank you very much.
Thank you very much to you as well. It was an excellent presentation, very interesting, high-tech presentation and theme and topic related. So if there are some questions, you are invited, to the audience, to ask him or send an email maybe later. Well, if there are not questions, I'm sure that later will arrive. We will continue with the presentation. And now I call upon Noshin Kiambash-Rath, University of North Carolina of Greensboro, USA, to deliver the talk on native nanostructure sulfates from the wings of TBCen cicada sensitized yeast to antifungal drugs. So,
Hi.
Noshin, you are welcome.
Hi, how are you? Good evening, everyone. At first, I should say sorry because of my voice. Something happened for me. I used several medication to kind of speak for the conference. Okay.
We can hear you well.
Okay. Can you see my screen?
Yes, we can.
Oh, okay. My name is Nushin Kiambash-Rath. I'm a PhD student of nanoscience in Joint School of Nanoscience and Nanoengineering in the UNCG. I want to talk about native nanostructure surfaces that we have on the wing of cicada that synthesize yeast cells to react to antifungal drugs. At first, I want to start why we choose cicada. Many insects, including cicada, have nanostructured critical, but in our lab, we choose these 3 wings because we have from low to high aspect ratio that allow us to systematically test the effect that different nanostructured geometries have on yeast viability. And the first law, sorry, change it. Okay. The first law is the top row show the helium-ion macrograph at 68,000 magnification. Middle row show atomic force macrograph that give us better topographical information. The bottom row show the schematic figure of that pictures. And the last one show the contact angle between this figure and the surface. The first line is gas coated by gold. There is nothing on it, just some debris on it. The second line is the periodical cicada wing coated by gold. And it displayed a spherical caped conical protuberance, but that with a mean length of 183 nanometers and a mean cap of 57. The third one is annual dog-day cicada that coated by gold. It's more like a spherical capped cylinder, and we have more contact surface. And the last one is common sand dog dragonfly that coated with gold. In this way, in this one, we have more contact surface with the, we have more contact surface in this one. The last line show the contact angle. And in each case, this nanostructure increase the total surface area when we compare them with the gold-coated glass as control group. And here we showed that the yeast cell, when they connect with the nanostructure surface ruptured happen for them. But as you can see, some of them are alive here. At first, I should say what happened for the yeast cell to make them to be disease in our body, because we have some of them in our body and they live with us without any problem. The first step that happened for them to make biofilm is adherence. It takes 60 to 90 minutes. And then in the next step, it's followed with initiation. They connect to each other and make long filament that help them to change from the yeast growth way to the pro-hyphae formation. And then they connect to each other and mature in a large and big filament. And they continue to do it again and again and make them to make a disease in our body. When we use adhesion stress and mechanical stress at the same time for the yeast cell on the non-surface structure, we found some of them ruptured, but we have some of them that they are alive, as I said before. And we want to know what happened for them. There are some other reason, because all cells not ruptured, so maybe nanostructure surface changed the biology of the yeast cells. So what happened for them? So we make these 3 experiments, and we compare our experiment with 3 control group. The first one is flat settle control that just let yeast cell to grow on the surface. The next group, we have mechanical shear control group that the yeast cell pass through the silicone tube. And the third group was anti-adhesion control that we add propylene glycol to it as an anti-adhesion factor. And the last one is our group that, as you can see, there is a wing on it. After 2 hours, we check the biology of them. It's there are several raw data here we have as a result of our experiment. We compare these 3 groups that we have. And for example, for nanostructure surfaces, we have around 5 gigabyte raw data, and total number of raw reads that we have, it's around 30,000 numbers. And total genes expressed in this group, we have 6,500 genes. But the more important part is how genes express differently in these groups. For nanostructure groups, we have 178 groups that express differently, but we have more in the anti-adhesion and mechanical shear. When we compare them and show with a heat map visualization graph, we found total completely different expression happened for them. We choose 50 more important gene expression in each group. Because of that, the genes is different for each group. We choose 50 genes for each group and compare them expression what happened in them. The red line shows upregulated genes, and the blue one shows downregulated genes. The most important part for the gene expression is the gene that was similar in different groups. Because, for example, for a nano surface structure group, we have 178, as I said before. 101 is up-regulated genes and 77 of down-regulated. The most important is this 10 and 38 and 12 genes that express the same in all groups. When we check it and found which all genes that express differently is a response from which part of the mechanism or biology system of the cells, we found most part is from the metabolism and the mitochondria part of the cells. And we check the genes that upregulated happen for them. Most of them are related to TCA cycle and oxidative phosphorylation and amino acid metabolism. But for downregulated, it's related to DNA replication, cell cycle, amino acid metabolism, and ion homeostasis. But the most important is ergosterol biosynthesis, because ergosterol is the target of antifungal drugs. So we just focus on it to how we can use nanostructure for yeast cell that increase the efficacy of the antifungal drugs on these kind of yeast cells. At first, I should say, what is ergosterol? Ergosterol is a sterol that is a member of the yeast cells, is the same as cholesterol in animal and human cells. And as I said before, it's a target of antifungal drugs. When we check that genes, we found 4 of these genes that we found it's downregulated. It's in the pathway of ergosterol biosynthesis. And as you can see, I mark all of them by blue line. And we found its effect on ergosterol biosynthesis. But, sorry, but because it's very important for us to know, is the pathway of ergosterol completely shut down or not, we add flipping as a dye to the experiment and then check it again. And it's our result. But we found some more information. We found after 2 hours, as you can see, we have more ergosterol exists in our nanostructure surfaces. But after 18 hours, we have less amount of it. We did it several times and we found we have a peak at 2 hours and then decrease, because ergosterol has a negative control on your on themselves. Antifungal, we have different antifungal drugs, as you can see here, and we just focus on azole and choline because it connected to ergosterol exactly. The azole work with the effect on the ERK11 product genes, and the choline exactly connect to the ergosterol on the membrane. So we choose these 2 antifungal, and after doing several experiments on different antifungal drugs, we make these experiment for our experiment. So at first we culture C. albicans and make them 2 different groups as a control and as our experiment, and incubated them for 2 hours, and then added antifungal drugs, and then incubated them again for 18 hours, and then make a control group and nanostructure group with different dilution, and then again incubated them to make a growth stem, and then read the result. It's a result, and as you can see, in different dosage of antifungal drug, in the control group, you can see several yeast that they are alive after 18 hours. But as you can see in our experiment, it's the lowest amount of antifungal drug. And when there isn't any yeast in these dilutions and nothing else in other concentration of the antifungals. Summary up to now, we found 178 genes in nanostructure respond, and some of them reflect to mechanical and anti-adhesion challenges. As I said to that graph, there are overlap with mechanical and anti-adhesion stress. And we found nanostructure surfaces respond metabolic changes in the yeast cells, and ergosol biosynthesis is a target of nanostructure surfaces. For the next step, we should work in some other nanomaterial that make similar changes, and found what cellular stress response is responsible for these nanostructure surfaces. In addition, we work in nanofiber mat. The first one is polyacrylonitrile film. This one is polyacrylonitrile microfiber, and this one is polyacrylonitrile nanofiber. And we found when we use a nanofiber, the rupture happened for the yeast cell, as I show here. After 8 hours, we have a growth for all that 3 groups, but we have the low rate growth for the nanofiber group. Why it stopped working? I can't change my slide. I don't know what happened, so I can't say by myself. We said we can maybe in the future, when we found the best nanostructure, nanomaterial that help to the antifungal drugs, maybe we can add them to this nanofiber, and then we can make some coverage or bandage for some people that have a burn, or after surgical they have they need antifungal coverage for their wounds. So we can add these two experiment and find the best material. I don't know what happened for my slide. Do you have any idea to help me?
Well, it is maybe the program that was stopped, but if you give it a few seconds, if not, you can finish. We are on time, and you can finish as best as you can. Remember us what is the conclusion, but don't worry.
Okay. For the next step, we want to use some other nanomaterial like silicon oxide, and found how they can affect on the growth of the yeast cell and biofilm forming for these kind of cells, and then add some of them to each other and find maybe in the future we can modify the antifungal drugs that exist now, and maybe add it to some other coverage for different disease, for the skin, especially for the skin wounds. We can add both of them, and then I can say thank you all, and thank you my advisor, because he helped me a lot, and thank you all of my all researchers in our group. If there is any question, I can answer.
Yes, of course. I think that if the audience have some question, you can ask her right now or send an email later. Thank you very much, Nushin.
Thank you. Thank you for inviting.
Well, the next speaker, it's me. I am Guillermo Bracamonte. I am from National University of Cordoba. I will talk about tuning high electromagnetic fields from the nanoscale toward the far field for nanophotonics and biophotonics applications. So, if you can hear me and as well check the slide. Now you can see the slide. Someone, can you tell me if it is there, the slide? Oh my gosh. I think that it is stopped. It is a problem, but we will give a second. I don't know what is happening.
Hello, sir. I can see you, but not the slides.
Not the slides. Okay, but you can hear me.
Yes, yes.
Okay, I will try to put the slide in the right place. Give me a few seconds.
Okay.
It is stopped, so I hope that it come back. If not, we will continue until the program responds. It doesn't work. So the problem, it was stopped. It's there. I'm sharing the screen, and there it was stopped. Well.
Yeah. Hello, doctor. May I know the issue? Can you double click on your screen?
Yes, I am trying to share my screen, but in my
Can you just go back? Can you just stop sharing screen first? Stop sharing screen first.
Now it is okay. Now it is okay.
We are unable to see your presentation. Can you double click on your presentation?
Wait a second. I will stop the video. Maybe there is some issue with that.
Yes. That's fine now. Just click on F5, presentation mode. F5.
Yes, I'm trying to do it. You're trying to do
Now
the
we are
best,
able to see your slides there.
Okay, thank you. Well, I will try to
press F5 key in your desktop keypad. F5 button.
Okay.
Doctor, can you hear me? Can you press
Yes,
F5
yes,
key?
I hear you. Yes, F5, okay. But it is.
Yeah, in
I don't
the
know.
footer, you can just see 80%.
Yeah.
There you
I'm
can,
trying to.
there is a funnel button. Click on the funnel button.
Yeah, wait a second. There. Well, I will try to give the presentation like that. I think that I will be able.
Yeah, not a problem. You can go ahead. Thank you.
Okay, so sorry about the delay. So I will talk about tuning high electromagnetic field from the nanoscale toward the far field for nanophotonics and biophotonics application. And in this context, should work the slide. Yes, we are we are working on design optoactive material from the nanoscale, but looking towards higher sizes, looking for generation of classical light from the near field interacting with, in the near field with optical active materials. So if we talk about optical active material, we have to talk about the nanomaterial for nanophotonics, and with consequent applications such as nanobiphotonics, neurophotonics, nanomedicines, nanopharmaceutics, nanobiotechnology. There are a lot of chemistry involved, even if we are talking about physics. For this reason, we are working with different fields, working together in order to mix chemistry, optics, and biophotonics. So the nanochemistry should be controlled in order to target application, but from fundamental research that it is related with synthesis of metallic nanoparticles as well chemical modification. So if we talk about hybrid nanoparticles and the property of these nanoparticles, first, I have to present one of the first Nobel Prizes in 1952, given to Parcel and Bloch from United States and Switzerland. They work focused on the manipulating and analyzing movement of subatomic gyroscope, such as proton and neutron, applying varied electromagnetic fields. In the next step in this research work, it was applying optical resonators that are confining these particles in the micro-sized particles in this case, but confining nanoparticle between two metallic slides, and applying the varying the electromagnetic field. They checked that they could generate variables and high intensities of electromagnetic field from these micro-sized particles. From this beginning, with the Nobel Prize, it was then continue working with reducing sizes, and it was generated a new research theme that it is area that it is plasmonic. That plasmonic is more related with surfaces, metallic surfaces, and nanoparticles, in particular that I'm showing here. So the plasmon, or high electromagnetic field that are generated from the electronic oscillation when it is excited, these particles, with an electromagnetic field, it could be tuned different wavelengths, such as here I'm showing, such as aluminum, gold, silver, with different intensities in different regions of the electromagnetic wave interval. So in this case, I'm showing you a type of gold core shell nanoparticle modified with the laser dye in their surfaces that could be tuned their intensities by metal enhanced phenomena that I will explain soon, and switch on off, but depending on if it is present or not this gold core. In this context, this nanoparticle, if we can tune the electromagnetic field and couple we can get a coupling with the surrounding, we can modify chemistry, we can modify properties, and we can develop enhanced emission as well enhanced semiconduction that it could be transferred to the bio application. And moreover, this nanoparticle, as you know, the nanoscale, it's very challenging in the way that if you control the chemistry, you can disperse or you can nanosynthesis. So now we are
Hello, am I audible? Hello. Hello. Hello, can you hear me?
Hello, I can hear you.
Yeah, it seems the last speaker had some technical issues, and so we will stop his presentation now. And the next speaker, I would like to call Amine Gainer from Sivas Cumhuriyet University, Turkey, to give a presentation on investigation of AIN and SI distributed drag reflector for vessels and telecom wavelengths. Hello, Amine, are you there? Hello, can you hear me?
Hello, now can you hear me?
Yeah, we can hear you. Yeah, please, you can start your presentation now.
Actually, I have problem about voice.
Okay.
And actually, I will start 20 minutes later, right?
Yeah, if you're ready now, you can start it now. If you're not, then you can move to the next speaker. Hello. Can we move to the next speaker?
Yeah, we can.
Yeah, okay. So now I'd like to call Mohadesh Madada Zaveri from Shahid Kamran University, Iran. And she will be presenting on the topic of freeze casting at ambient pressure, a step to facilitate the process of fabricating porous materials such as graphene, CNTs, imagers. Yeah, can you hear me?
Hello everyone. Yes, I can hear you loud and clear.
Yeah, very warm welcome to you, to our concert. And now you can start your presentation.
Now I should share my screen with you.
Yeah.
Of course. Just a second. Excuse me, I just need some minutes. I'm sorry. I cannot share my screen. I have a problem with that. I believe someone has shared the screen before me. I believe.
Okay, let me check once again.
They should close the sharing screen so I can share my screen. Sorry. Can you see my screen now? I'm so sorry. Can you hear me? Can you see my screen?
Yeah, we can see you.
Yeah. Okay, now I start. Good afternoon, everyone. My name is Mohaddese Madadi Jaberi. I hold a master's degree from Shahid Kamran University of Ahvaz, Iran. And currently, I'm working as innovation and technology expert at Khuzestan Science and Technology Park. I'm so delighted to be here today among such esteemed scientists and experts at Nanoscience and Nanotechnology Congress. As a researcher in this field, it's an honor to have this opportunity to share my knowledge and insight with you. My presentation entitled Freeze Casting at Ambient Pressure, a process of fabrication porous material such as graphene, carbon nanotubes, or gel. In this presentation, I would like to give you some brief introduction, experimental details, results, and discussions, and lastly, the conclusions. So what is graphene? We all know graphene is a set of carbon atoms formed as a hexagonal honeycomb structure on a plate. And we all know the fabrication methods, which is such as micro-mechanical exfoliation and CVDs and some chemical method like oxidation and reduction.
Sorry for the interruption. Actually, we can't see your slides. Maybe we can try switching between the tabs. Actually, we can see the Zoom link itself.
You cannot see the slides?
Yeah, we can't see the slide actually. We can see your Zoom screen. Yeah.
I believe now you can see the slides.
Yeah, now
okay?
we can see. Now, yeah.
Okay,
Thank you.
okay. I'm so sorry. I was talking about the fabrication method of graphene and the unique properties of graphene, which all we know about that, the high thermal conductivity, high mechanical strength, high optical transparency, and so on. On the other hand, we have 3D graphene structures, such as graphene aerogel, which made of 2D graphene sheets with specific electrical and mechanical properties, which have many applications in the field of energy, sensor, and to name but a few. Graphene and CNT's hybrid aerogel are a 3D network of graphene, which composed of CNTs. There are three types of the hybrid of graphene and CNTs, which you can see in the picture. And the question is that what is aerogel? Aerogel are spongy solids with an interconnected nanostructured network with high porosity. High porosity, I mean by high porosities above 50%, low densities, and largest specific surface area among non-powders. We can mention graphene CNT's hybrid aerogel as example for carbon-based aerogel, which I mentioned before. There are 3D networks of graphene composed of CNTs. So, what is the method of fabrication, the method of aerogel fabrication? The first step is to make and prepare the hydrogel. Then we should replace the fluid inside the hydrogel with air. But this step needs some specific methods of drying. So we have to be careful about the volume and structure that should be unchanged. You know, it shouldn't be collapse. It shouldn't collapse during the drying. So, as I mentioned, we should pick very specific and unique drying method of unique method of the hydrogel drying. As you can see, according to pressure temperature diagram, we have three kind of drying method: critical point drying, freeze drying, ambient pressure drying. We all know that critical point drying and freeze drying are somehow costly, and they need special laboratory equipment. But what about ambient pressure drying? At ambient pressure drying, we can say this method actually doesn't need any special equipment, and it somehow need low cost. It is so low cost and eco-friendly, and gives us the possibility to produce aerogel, graphene aerogel, in a large scale, of course, without any collapsing and shrinkage. All we need is to pay attention to the Laplace formula, which you can see here. P is the capillary pressure, and R, they are so important for us, is the radius of the pores produced inside the hydrogel. we should, of course, we should reduce the capillary pressure, and it can be happen when we increase the radius of the pores produced inside the hydrogel. That can be happen with freeze casting method at, of course, ambient pressure drawing. And now I have to, sorry, one minute. I have to mention some information about freeze casting. So what is freeze casting? Freeze casting is a very simple, inexpensive, and environmentally friendly method to produce of some porous materials. In this method, as you can see, all starts with colloids. We have colloids, and we start to freezing these colloids, and we somehow grow crystals in these fluids, and the colloids have to, the particles of colloids have to concentrate. After the drawing, we have the colloids, concentrated colloids, and of course without any collapsing. This method is divided into two categories: anisotropic for non-directional porosity, and isotropic for unidirectional porosity. Which in our study, in my study, my purpose is to use this category, unidirectional porosity. And for that, I have to use some materials in my experiment, which you can see here. I give you some minutes to look at the materials. And of course, several devices I used in this study, which are shown here: a simple oven, ultrasonic centrifuge, and I believe everyone is familiar with. But I needed, as I mentioned before, I needed the crystals to grow unidirectionally. So I set up a device applying basic physics rule. I used a container with walls and a cap made of plastic, and I wrapped them, this area, with foam to minimize the heat which can transfer, and use a metal plate for the bottom, which has a high heat conductivity. Then let this metal, let the bottom to be in touch with liquid nitrogen, and the hydrogel inside the container can be freezed from the bottom. And I believe this setup was an added value to this method. For characterization systems, some systems are used here: XRD, SEM, and UV visible for mechanical experiments and electrical conductivity experiment. I have to set up a system which you can see here. And for calculating the absorption capacity of oil-based materials, I used a very simple equation, which you can see here. And for the densities and porosities of aerogels, I use this simple formula, and you can see the reference of this formula. And for experimental section, of course, for the first step, I have to prepare the graphene oxide by modified Hammer's method, which all familiar with. And I don't bother you with the extra explanation. And then I have to functionalize the single wall CNTs. And after that, I synthesize graphene aerogel by freeze casting method. I use 10 milligram of graphene oxide solution with a concentration of 4 milligram per milliliter, and added 80 milligram elascorbic acid as reducing agent, and put it at the oven for 1 hour and at 95 centigrade. The obtained hydrogel was a partial reduction, PRGH here, and I put this PRGH in a vessel, in a setup which I mentioned before for freeze casting, and put it placed in a freezer at minus 20 centigrade for 48 hours. The obtained hydrogel have to completely get completely reduced. So I put it at oven for 5 hours and at 95 centigrade. And now I have RGH or completely reduced graphene hydrogel, and it is now ready for final step, and I heated it at 60 centigrade for 1 day, for 24 hours. And after that, I have graphene aerogel. The final experimental section was the synthesizing of graphene single-wall carbon nanotubes aerogel by this method, freeze casting method. I use exactly the same process of fabricating this aerogel like graphene. But with very simple different. I use 10 milliliters of graphene oxide solution at concentration of 4 milligram per milliliter, and I added 10 milliliters of functionalized single-wall carbon nanotube solution at concentration of 1 milligram per milliliter, and the process proceeds with sonication and adding the reducing agent to solution, and heating, and of course freeze casting, and the obtained hydrogel was heat again for completely reducing hydrogel, and the final hydrogel was heated for 24 hours at 60 centigrade and obtain graphene single-wall carbon nanotube aerogel. You can see the final products. This picture is graphene hydrogel and graphene aerogel. This picture is graphene single-wall carbon nanotubes, hydrogel and aerogel. You can see some of SEM images of graphene aerogel and graphene single-wall carbon nanotube aerogel. Table 1 is presenting the some structural characteristics like average pore size, which I calculated from with Digimizer software, and density and porosity with some simple equation which I mentioned before. You can see that single-wall carbon nanotube, when I added single-wall carbon nanotube to graphene and fabricate the aerogel, you can see that it somehow influenced the some structural characteristics like density and porosity and average pore size. Now I have to compare the XRD patterns. You can see that this image is the XRD patterns of 2 aerogels which I fabricated, and this image, the right image, is the XRD patterns of reported patterns. which you can see both peaks for graphene oxide and reduced graphene oxide in both samples, in both samples XRD patterns. At 2 theta equal 9 degrees and 2 theta equal 24.3 degrees. After that, I try to evaluate, to examine the mechanical properties of the samples. As you can see, sorry. As you can see, I try to put some weight to my two samples, two aerogels. The weight are different from 2 grams to 200 grams, and I measure the stress and strains of graphene and graphene single wall carbon nanotubes. I believe you can see the pictures, figure A, which shows represent the stress versus strain for both aerogel, and figure B can display the height recovery of both samples due to applying stress over time. After that, I try to measure electrical conductivity. I have to produce same size of aerogel and connected them in electrical, connected them to electrical connection. Figure A to D show the current versus stress and resistance versus stress graphs for 2 samples at 3 different potential, 2 voltage, 4 voltage, and 6 voltage. This part of experiment was so interesting for me. I try to measure absorption capacity and reusability of these samples. I used 4 different oil-based material like gasoline, kerosene, cooking oil, ethanol, and I immersed and saturated my samples, 2 samples, in these liquids and squeezed them and do it for 4 cycles. That was so wonderful for me, and you can see the result here. The table 2 show gasoline absorption capacity for graphene aerogel. That in that way I can show that how I measure the absorption capacity. And after that, I try to measure dye absorption of these 2 samples. I used 10 milligram of both aerogel. They were homogenized in dark with methylene blue or MB, and then UV spectrum of methylene blue with samples were taken and recorded every 15 minutes. Figure B, A, and B present the UV visible curves of methylene blue absorption by both samples, and figure C displays both C over C0 versus time diagram, where C0 is the initial concentration of the dye, and C is the concentration after degradation over time. As conclusion, you can see some of the conclusion here. First, mechanical experiments show that both aerogel can withstand a strain of up to 90%, but in general, graphene single ball carbon nanotubes aerogel have a greater elasticity than the pure graphene aerogel. About the electrical conductivity, we somehow conclude that graphene aerogel have better electrical conductivity than graphene single ball carbon nanotube aerogel. And we saw that the electrical current increased almost linearly by applying stress. About the absorption capacity of oil-based material, those two samples capacity was measured, and somehow gasoline was uptaken the most by both samples among 4 studied liquids. And about the absorption capability of both aerogel, somehow we saw that they are the same after 3 hours. It is possible to use them repeatedly, so we can use them as dye removal from water and wastewater in industries. This was an abstract of what I have done through my master's years, and I'm looking forward to investigate more in this field as a PhD student. And if you found my presentation interesting, you can read our paper, which have been published recently. And this is my email for further question and collaboration. And at the end, thank you for your attention, and I'm ready for questions.
Thank you, Mahadesh, for your wonderful presentations. It was truly enlightening. And I now request anyone who has questions can come forward and ask questions so that we can really
Thank you.
Okay. In case there are any questions, and if something comes up, they can message you in the chat box or definitely can email me. So thank you, Mahadesh, once again. Now we shall move to the next speaker. Now I would like to call our moderator for our event, Mr. Galerni. Due to some technical issues, he was cut off from the meeting. Mr. Galerni, you can start your presentations.
I am here. I am Guillermo Bracamonte. I don't know if it is my time to speak.
Yeah, you can start your presentation.
Okay, sorry for this last inconvenience. I hope that now it works. Please let me know if you are hear me well, and as well see if you are seeing my presentation. I don't know.
Yes, we can hear you properly. And
okay,
yes,
so
presentations are visible. Yeah.
Perfect. Well, I begin. So my presentation, it is about tuning high electromagnetic field from the nanoscale toward the far field for nanophotonics and biophotonics applications, focusing on core shell and hybrid nanocomposite. In this context, as I told you, well, we are looking for designing of optoactive nanomaterials where radiation matters interaction take place in order to develop nanophotonics to generate non-classical light, but contributing with a high impact by a near field that it is acting on the hybrid composite. In this context, we have to talk about the design of nanomaterial and application for nanophotonics, that it is extended to nanobiophotonics, neurophotonics, nanomedicine, and nanopharmaceuticals, as well as nanobiotechnology. We are all looking for this type of application. And as you can see, we are mixing different research fields such as chemistry, optics, and biophotonics, where the nanochemistry, in this case, is the main research field to begin to develop nanophotonics materials. So we will talk in this presentation about metallic nanoparticles, silica modification, core shell nanoparticles, with different type of chemistry modification, as well with material incorporated, and related potential phenomena, physical phenomena, that I will explain soon, that it could enhance emission and matter interaction. So in this context, first I present the Nobel Prize of Purcell and Bloch, that is what related with manipulating, analyzing subatomic gyroscopes, such as protons and neutrons. And this particle that could be controlled by electromagnetic field, and it has a consequence with many different type of instrumental analysis that based on imaging today. It was continued working, and it was modified this interaction with the electromagnetic field, adding two slide metallic slide, and by this manner they enhance and they obtain spontaneous emission from this metallic particle from the micro-sized scale. In this case, we are concentrating and we are focusing on a metallic nanoparticle. Metallic nanoparticles could be generate varying the electromagnetic field on their surfaces, and generate electromagnetic field, high electromagnetic field in the varied wavelength intervals, such as here I'm showing for aluminum, silver, and gold. And by this manner, and tuning the nanoscale, we can put, as it is shown here in this schema, from the gold core, we modify with silica spacer after adding a emitter to convert this nanoparticle in nanoemitters, that it is enhanced by the plasmonic core due to the interaction with the electromagnetic fields generated. As well, it could be switch off this phenomena, control the phenomena, and as well optimize the phenomena. All this research is currently being done. It's not all already known. So the control of distance, concentration of the fluorophore, and related physical parameters and theoretical studies are currently in progress. So our first insight, it was modifying the gold nanoparticle with varied silica spacer. As well, we are thinking about enhanced semiconductive property that it could be obtaining. But all these phenomena focusing on the precision medicine and looking for bioimaging application within cells or nanobiolabeling application. The first challenge that I have to mention in the nanoscale, as you know, or that you work with nanoparticle, it is the interaction between them. It should be controlled, and depending on the chemistry that it is added, it could be as well modifying the phenomena, the physical phenomena and chemical phenomena, as well with the interaction with cells, looking for biophotonics application. So very briefly, we can highlight different type of gold nanoparticle synthesis, such as this one by green chemical method, as well by the well-known Turkevich method, that it is a citrate reduction reaction, that it is work very well. And it could modify, it could be modified the surfaces by adding a silica spacer, molecular spacer as well, in order to get this core shell nanoparticle that I am showing here, that we can put different emitters and add a different length from the gold core. by this manner, control the phenomenon, control the effect, and study quantum shield emissions, and as well the effect of the core by digesting the gold core with a sodium cyanide methodology, that is a digestion method. And this approach that I'm showing with silica, it could be extended to other type of polymer, biopolymers, biodegradable polymers. Here I'm showing the biopolymer as well with other types of core shell with smaller nanoparticle close to the quantum level and quantum sizes. And these sizes could be extended in order to transfer energy through space and times, such as these multi-layers nanoparticles. And of course, then we modify the plasmonic core with different type of silica spatial length, as well chemistry. This plasmon could be modified. And by this manner, if we optimize, recently we published a paper with in collaboration with Professor Boudreau from Laval University in Canada, that it was modified with Ramin B with the same schema that I showed before. And in this nanoparticle, we are able to get very strong small dot close to the quantum scale, focusing very well. That this nanoparticle very ultraluminous and present just only with the metallic core, and absent they are switched off. So controlling chemistry as well, we can get higher sizes, high intense luminescent particles. And of course that this could be checked as well, that their stability could be measured by fluorescent lifetime decays. Shorter lifetime decays, it could be obtained from optimized nanometers. And by this manner, the main interest from us in this case, immediately it was if these properties it could be applied to be tracked in real time and in continuum flow movement. So the nanoparticle, the question is if the nanoparticle should be static or can be moved and be tracked by different spaces. So it was applied in flow cytometry and fluorescent lifetime decays, measuring, correlating colloidal dispersion, different concentration, different type of aggregation. That is shown here in this first page of this recent publication as well. So the title is related with inflow nano-optics from the near field to the far field, focusing on this this phenomena that it is metal enhanced fluorescence, right? So the schema, highlighting the schema is track the nanoparticles through continuous movement and correlate this state with a state in continuous movement with laser fluorescence microscopy, as well correlating properties obtained by other type of characterization in order to quantify if they are still being there, these properties, ultraluminescent properties. So in the first observation, it was that this nanoparticle could be tracked, could be detected by just inflow cytometry, standard, advanced or standard inflow cytometry, even without imaging methodology, it could be tracked, and it could be differentiated different distribution, such as here I'm showing, depending on the laser excitation applied. So standard or advanced inflow cytometers are available to switch off and switch on different type of laser, and by this manner could tune the excitation of this gold core and getting different nanometer detection and counting. So the nanoparticle were as sensitive as well as the cytometer. It was high sensitive as well to detect silica spatial variation within the nanoscale between 10 nanometer and 20 nanometers. This is difference that I mentioned, they are too short, and really we were working with 5 nanometer to 10 and 15 and 20 nanometers. This difference that could be observed by laser fluorescence microscopy, could be observed difference between the nano emission. It was able as well to detect varied counting of nanometer by inflow cytometry. So the instrument showed very well capability to detect very small difference within the nanoscale, varying the silica spacer, as well concentration of the laser dye incorporated on the surface of the nanoparticle, but as well the nanoparticle as well, it was showed a very accurate control that provided the opportunity or the possibility to the instrument to detect these nanoparticles. In absence of the gold core, the distribution, as you can see here, the distribution of nanometer detection of fluorescent emission, it was very drastic, modified and diminished. And by this manner, it was confirmed that the inflow cytometry parameter could be tracked, and it even in some cases could be improved because we detect single nanoparticles at time. And looking for that, in collaboration with Laval University in Canada, it was possible to put this nanoparticle within a controlled optical nanosystem different to the inflow cytometry. But in this case, I will not speak about detail of the optical setup, but it was part of another thesis of Danny Brouard and Denis Boudreau as well. So they work on this optical setup in order to detect image with high resolution in order to detect single nanoparticle. As you can see here, we can detect, exciting with the right laser excitation, we can detect single nanoparticle as well higher sized nano aggregate. And from this analysis, it could be obtained other enhancement, and other characteristics. So we are studying this type of nanoparticles characterization by in continuous movement. So in order to bioapplication, but in this case it was applied to the modification of Escherichia coli. Escherichia coli, as you can see here in the figure A, they are non-optical active, but when you control the chemistry and when you can vary concentration, you can modify the bright field microscopy resolution, as well, of course, that the electronic transmission microscopy. So confirming and publishing before some publication related. Then optimizing effect and phenomena, it was possible to create a procedure, a methodology to obtain a nanobio labeling that it was enhanced at varied concentrations of a nanoparticle, even arriving to detect single bacteria with a very high resolution and details. So these properties, by this manner, it was able to transfer this property to the biosurface, and it is possible in this moment to get maybe inside the cell, the membrane within the cells, and we are studying this effect, looking for perspectives, and in order to conclude if it is possible to incorporate this type of nanoparticle within cells in order to use these nanoparticles as nanomicro devices for inflow application, but looking for within the cells. These particles, these nanoparticles, ideally we can present this nanoparticle as a nanolaser or nanobiolaser, depending on the application, and with an enhanced resolution, looking for the first step, it was achieved that it is the biodetection, enhanced biodetection by different colors. The second one, it was obtain a nanoparticle across the membrane. We are working on that. And in the next one that we have a previous publication that is related with a silica nanoparticle in Absenov's gold cores, but it was able as well to transfer energy through the unicellular microorganisms, targeting organelles from outside to inside. So in this perspective, we are looking as well for organelle targeting, quantifying phenomena, biological phenomena within, that it is the challenge, looking as well for single molecule detection, biomolecular tracking, and of course, to get some insight within nanobiotechnology. And this work, it was done with in collaboration with many research groups and different universities, and as well as part of a startup and recent group research after my many postdoc position, obtaining different places that you can check that in these flags. And we are doing a lot of stuff, and we're starting as well to interact with other people. You are invited to get some feedback if you are interested to collaborate or ask some question related. I think that I am on time. I thanks a lot for the organization, to this opportunity to act as a speaker, as well to collaborate as a moderator. So for me, it is all at the moment. I am waiting for your questions, and I will stop sharing the screen.
Thank you, Mr. Guillermo, for your very good presentations. And if anyone has questions, they can come forward and ask your queries.
Okay. I think that it's okay. So the next speaker, I think that it's I'm trying to put there I stop share. Yes, okay. Well, the next speaker, Asif, yes, I call upon Rizwan Asif, Karachi University of Pakistan, to deliver his talk about green synthesis of silver nanoparticle, structural characterizations, and their antibacterial potential. I don't know if he's there. Dr. Rizwan?
Emine Kaynar.
Yes, I am here. Please give me just 2 minutes.
Maybe there's a miscommunication. I would like to first invite Ms. Kate to continue with her presentation. Dr. Asif, you will be up next. Hope you understand. Ms. Kate, you can start presenting. Yeah, thank you. Thank you for understanding. Ms. Kate,
yeah, I'm here.
Yeah, welcome to our session.
And also, can you hear me?
Yeah, you're audible perfectly.
Okay, because I'm using 2 sites on PC and my phone.
Okay. We can hear you.
Okay. So sorry. Now, can you see my screen?
Yeah, we can.
Okay. Hello, I'm Emine Kaynar. I'm a nanotechnology engineer, and also I have bachelor master's degree in nanotechnology engineering at Sivas Cumhuriyet University. And now I will start doctorate with Clara Sarajana in Germany. My work titled as Investigation on Aluminum Nitride Silicon Distributed Bragg Reflector for VEXELs at Telecom Wavelengths. I will start with introduction and then literature studies, characterization results, and I will final with conclusion. Laser, which stands for light amplification by stimulated emission of radiation, is an optical device that creates and amplifies a narrow dense in-phase monochromatic light beam. The first laser has been produced by Theodor Meinmann in 1960 based on the theories of Charles Stones and Arthur Shallow. Later in 1961, the first semiconductor laser, also called diode laser, has been made in America by Robert Hall. Semiconductor lasers are classified according to where the radiation comes out. H-emitting laser. In an H-emitting laser, light is emitted from the edge of the substrate. A solid-state laser is grooved in a semiconductor so that the optical cavity is parallel to the surface of the plate. Surface-emitting laser. In surface-emitting laser, light is emitted from the edge of the substrate. A solid-state laser is grooved in a semiconductor so that the light comes from like that. Compared to surface-emitting laser and H-emitting lasers, surface-emitting lasers have several advantages: circular beam, low threshold current, easy patch shaking, and high efficiency. Vertical external cavity surface-emitting laser, also called VCSELs, emerged in the middle 1990s to address problems with conventional semiconductor lasers in order to achieve watt level optical powers with circular beam geometry. This figure shows the basic configuration of VCSEL. DBR and output coupler are used as resonator mirrors. The job of the output coupler is to reflect some of the radiation from the VCSEL to chip back to the chip, thus providing resonance and radiating small parts as laser radiation. And also you can see from this figure, VCSEL consists of active region and DBR. DBR, distributed Bragg reflectors, also called distributed Bragg mirrors, are obtained by repeatedly growing two materials with different refractive index on top of each other. Two layers with high refractive index and low refractive index, respectively, are defined as a pair, and the number of pairs determines the maximum reflectivity of the DBR. Layer thicknesses should be 1/4 of the working wavelength for constructive interference to occur. The number of pairs required to produce a highly reflective mirror depends on the refractive index of the layers of a pair. Pairs are required for two materials with a large refractive index difference. One of the most important parameters in the DBR structure is the bandwidth. The bandwidth between two wavelengths in which the reflection obtained the DBR structure exceeds 90% is called stop bandwidth. A DBR structure with a large stop bandwidth is important for better efficiency of the laser device build. If we look at the literature studies, one of the studies in the literature has been done by Heynen et al. 100 watt power has been obtained at 1000 nanometer. In this study, gallium arsenide, aluminum arsenide is used as the DBR structure, and gallium arsenide phosphate, indium gallium arsenide quantum well is used as active region. As a result of this study, the highest output power has been obtained around 1000 nanometer wavelength. The other study has been done by Lindberg et al. In this study, indium phosphate, indium gallium arsenide is used as DBR structure, and indium gallium arsenide phosphate, indium gallium arsenide phosphate quantum wells have been used as active region. As a result of this study, 100 milliwatt power has been obtained at 1550 nanometer. But as can be seen from this figure, multimode radiation has been obtained. The reason for this is that the diamonds used as a heat spreader causes the echelon effect. The other study has been done by Ratuinan et al. Here, aluminium gallium arsenide is used as DBR structure, aluminium gallium indium arsenide, quantum wells are used as active region. As a result of this study, 2.6 watt power has been obtained at 1570 nanometer, but as can be seen from this figure, multimode radiation again has been obtained. Light of different colors shows us that is the multimode radiation. The reason for this, the echelon effect, as in the previous study. Another study has been done with Ratuinan et al. Here, aluminium gallium arsenide is used DBR structure. Aluminium gallium indium phosphate quantum wells are used as active region. The DBR structure has been grown on gallium arsenide substrate. Active region has been grown on the indium phosphate separately and then bonded with the wafer fused technique. As a result of this study, 4.8 watts power has been obtained at 1480 nanometer. But as can be seen from this figure, multimode radiation has been obtained. At the same time, in this study, the cost of growth is so high since two separate growths have been made in this study. The other study has been done by Merite et al. Here, aluminium arsenide, gallium arsenide is used as DBR structure, and aluminium gallium arsenide, indium phosphate quantum wells are used as active region. This study is technique is same at previous study, and also in here, DBR structure has been grown on gallium arsenide substrate. Active region has been grown on indium phosphate substrate, and then for the bonding, wafer fuse technique is used. As a result of this study, 3.65 watt power has been obtained at 1550 nanometer. And also in this study, cost of growth is so high because of the two separate growths have been made in this study. Finally, I will talk about the work done by Hopkins et al. In here, aluminium arsenide antimon, gallium antimon is used as DBR structure, and indium gallium arsenide antimon, aluminium gallium arsenide antimon quantum wells are used as active region. As a result of this study, 200 milliwatt power has been obtained at 2200 nanometer. There are two main reasons why gallium arsenide-based VCSEL performances could not be obtained in these studies. Semiconductors used in DBR structure have low thermal conductivity and low refractive index differences. Based on these studies, it's aimed to eliminate the problems of thermal conductivity and refractive index difference in this study. For this purpose, firstly, it has a high thermal conductivity and a high refractive index difference of the silicon aluminum nitride DBR structure is selected. And for the growths, we used sputtering system, and actually final of the our simulation, we have been grown we have been grown 6-pair silicon aluminum nitride. Looking at the SEM image, the layers are clearly visible and the thicknesses are in harmony with each other. And also in here, the reflectance graph of DBR 29 grown 6 pairs is given in figure. As a result of the simulation given in figure, the shifts in our layer thickness has decreased below 10%. 10%. This value is acceptable for multiple layers grown with this sputtering system. In order to measure the absolute reflectance, the reflectance measurement performed using a silver mirror is given in this figure. The reflectance value above has been reached above the silver mirror reflectance, which is accepted as a reference in DBR growth, has been reached. It is known that the absolute reflectance of the silver mirror is 98%. Accordingly, the absolute reflectance of DBR29 has been obtained as bigger than 99%. This value is quite sufficient for the DBR structure grown to be used in the Wexel structure. For higher reflectance, it is possible to obtain 99.9% reflectance by increasing the number of DBR pairs. Conclusion, there are two main reasons why gallium arsenide Wexel performances could not be obtained other studies. And so for this aim, we are selected the silicon and aluminum nitride DBR because for silicon and aluminum nitride have a high thermal conductivity and high refractive index difference, so that 6 pairs silicon aluminum nitride DBR has been grown, and from SEM image, the layers are clearly visible. And if we look at the reflectance results, we have been obtained bigger than 99%. In this study, a new material with extremely sufficient reflectance values for DBR mirrors has been developed and will be used in future Wexel studies. Thank you for your attention. If you have any question, I can answer to your question.
Okay, thank you very much for your presentation. It was very nice, and I'm sure that there are questions. If not, you can send her an email.
Yeah, actually, I have email under my presentation. Yeah, you can see.
Thank you.
You're welcome. Now, I will stop sharing my screen.
Okay, please. Please.
Thank you so much for inviting me.
Okay. So thank you very much. And the next presentation, I call up Rizwan Asif, Kharshi University, Pakistan, to deliver his talk on green synthesis of silver nanoparticles, structural characterization, and the antibacterial potential use. So if Rizwan Asif is there.
Hello, everyone. Hello, everyone. I'm audible to you?
Yes, we can hear you.
Okay, my screen is visible?
Yes, it is visible.
Okay, thank you. Hello, everyone. My name is Dr. Rizwan Asif. I am working as an assistant professor in Kharshi University in Lahore, Pakistan. And today I'm going to present one of my published article, which is green synthesis of silver nanoparticle from leaves extract of Moringa oleifera and their characterization and the antibacterial potential. So we start from the introduction. As we know, throughout history, there has been a battle between the human beings and microbes. And as a result of this war, the microbe caused the different diseases to the human beings. And against these microbes, especially I'm talking about the bacteria which are known as antibiotics. But unfortunately, due to excessive and misuse of these antibiotics, bacteria get resistance against these antibiotics, and themselves against the effect of antibiotics. And antibiotic resistance has become a greatest global threat of the 21st centuries. And is antibiotic resistance a problem? Yes, it's an threat. As I said in a previous slide, economic burden to the society. Here is the world mortality and approximately 7.5 to treatment failures, and so you can get how the antibiotic. In this slide, the timeline of antibiotic resistance is shown. However, the passage of time, antibiotic
Well, I think that Rizwan Asif, I don't know if he's there.
Yes. I'm audible?
No, it's okay. Did you finish?
No. I'm continuing. Still continuing.
Okay, because you are not sharing the presentation. For this reason,
I try
something
to
happened.
I try to again
just...
share it. I try to again share it. Maybe maybe I disconnect.
Okay, okay. Take your time, but please let us, if you can, what are you doing if you're trying to share an energy?
Please give me a second. No, it's visible.
Yes, we are looking. Oh yes, antibiotic resistance global.
Okay. Antibiotic resistance is a global issue. Exists in all countries, even both in high and income countries, like even in USA, UK, with a strong health system. Antibiotic resistance also exists in these countries. And in South Asia, like India, Pakistan, Afghanistan, Nepal, Bangladesh countries, nearly one newborn child dies every 5 minutes from bloodstream infection because the antibiotics given are not effective due to bacterial resistance. So due to excessive use of antibiotics and irrelevant and misuse of antibiotics, especially in developing countries, the situation has become very alarming. And nearly one newborn death occur in every 5 minutes. Well, here are some reports about the antibiotic resistance in different time periods, and conclusions of all these reports that we are losing war against microbes. So it's against a very alarming conditions. And the antibiotic resistance has become a complex global challenge for the community and a real issue for the sustainability of this planet. And nearly death rate will be reached up to 10 million in 2050, and the cost rate will be increased above 100 trillions. So there's a need of time to replace these synthetic antibiotics with some other source which is used to cure the microbes. So in this study, I used the silver nanoparticle, synthesize the silver nanoparticle from the Moringa oleifera leaves and use against these microbes. So Moringa oleifera is a plant which belong to Moringaceae family. It's a native plant in Pakistan, in India, and Afghanistan. The world most multi-purpose. It used for the different purpose, like it's immunomodulator, antimicrobial, and it even used for the nutritional purpose. And it has a lot of bioactive compounds, especially glucosinolate, which is well known for their antibacterial potentials. And the silver nanoparticle and nano word derived from Greek word which mean dwarf are extremely small. So, and the nanoparticles are the particle which range between 1 to 100 nanometer, and they consist of micromaterial in which active ingredient is dissolved, encapsulated, and absorbed or attached, and they show the active against the microbes. And there are different methods. There are different methods used for the synthesis of silver nanoparticles. Synthesis of nanoparticles. The most commonly used method are physical method, chemical method, and biological method. Physical and chemical method are expensive. Some are toxic effect on the environment and difficult to synthesize. So biological method is safe, cheap, and environment friendly method, which I adopt in these studies. And so further green synthesis or biological synthesis also carried out by microorganisms and plants. And again, nanoparticles synthesized from plants is preferred over microorganisms because microorganisms are not easy to handle and maybe are pathogenic and cause diseases. So plants are the preferred source for the synthesis of the green particles. So there is overall procedure or step used for the synthesis of nanoparticle, which start from the collection of plants, then extract prepared by dissolving powder of plants into the specific solvent. Then prepared extract was dissolved into the nitrate solution. Then stirring was done, and at the end the nanoparticle was recovered. For extract preparation from the Moringa oleifera leaves, the Moringa oleifera leaves are collected from the local botanical garden, and 10 gram
Are you there, Rizwan Asif? We are watching the green synthesis of silver nanoparticles from oleifera, but we cannot hear you and the slides are not running. So I think that Rizwan Asif has a little problem maybe with the connections. We wait him or us to the next one. Are you there, Rizwan Asif? Well, he's not there. I think that we can proceed. I don't know what thinks the organization, but we can go on with the next one. That it is, I call up on Seiko Jose Centralship and Good Research Institute, India.
Yes.
To deliver.
Can you hear me?
Okay. Seiko Jose, you are there. Okay. His talk on investigation on effect of nanocalonite as a filler in the coarse cool vinyl ester composite. So you are welcome, Seiko Jose.
Yeah, thank you. Can you hear me now?
Yes, we can.
My slides are moving.
Yes, your slide is going well.
Thank you very much. My topic is investigation of effect of nanokaolinite, that's a nano clay, as a filler in coarse wool vinyl ester composite. Our team consists of myself, Siko Jos. I am a scientist in Central Sheep and Wool Research Institute, Avikanagar, in textile manufacturing and textile chemistry division. Shraddha Maria Thomas, Jessia Susan Jost, Anjumol KS, and Professor Dr. Thabu Thomas. Now, just a bit introduction about Indian sheep breeds. Basically, the work is on coarse wool of Indian sheep. So these are some of the Indian sheep breeds which produces very coarse wool. Now, if we are classifying the wool fiber based upon the diameter, we can divide into two categories. First one is the fine wool, which is having below 20 microns diameter. Medium coarse wool is having 20 to 40 micron diameter, and coarse or kempi wool, which is generally having more than 40 micrometers. Now, the fine wool is getting employed in apparels and textile industries, and medium coarse wool is utilizing in carpets. Now, finally, the coarse wool, that kempi wool, since it is having brittle structure, modulation, and weak strength, it cannot be employed in both the above categories, so it is still underutilized. So my attempt is to give a value addition to this coarse wool by providing a technique which is composites. I'm coming to this one. So this is my motivation. As I told you, these shepherds, they are not getting any value for this very coarse wool. Sometimes they are even not getting the shearing cost. So my aim is to give a value addition to this one through wool polymer composite. Now, this is the sheep breed, that Patanwadi is the sheep breed which has been taken for the study. It is producing a coarse wool having more than 50 microns. So this is the objective of the study, to investigate the effect of nanokaolinite in the physical, mechanical, morphological, and aging performance of coarse wool vinyl ester composite. Now, coming to the materials and methods, we prepared vinyl ester wool composite having nanokaolinite as a filler. Different filler concentration has been tried: 0.25, 0.5, and 1% on resin weight. Now, this is the resin which vinyl ester is the resin. Some additives like accelerator, promoter, and catalyst has been added. After that, this resin along with the nanokaolinate was poured over the coarse wool fabric and uniformly spreaded over the fabric using a hand-driven roller. Now, I kept it inside a compression molding machine with 5 kilogram per centimeter square pressure and for 6 hours at room temperature. So this is the graphical representation of the process, where you can see the whole process: addition of nanokaolinite, addition of accelerator, catalyst, and promoter, then mixing, again coating on wool fabric, compression molding, and again the composite which are formed by this method has been characterized for different parameters. So these are the characterization I performed: tensile strength, elongation, impact strength, water diffusion, FTR, DMA, SEM, and aging. Coming to the result and discussion. W, you can see the abbreviations here. W means wool, NK means nanokaolinite, VER means vinyl ester resin. Now, we developed 4 different composites. One is without adding nanokaolinite, and second one is 0.25 nanokaolinite, third one is 0.5, fourth one is 1%. Among these, the tensile strength, highest strength, tensile strength was observed with 0.5 nanocovalent. Also, modulus was found to be the highest. Now, the elongation was found to be highest for 1%. Also, 1% is having the highest impact strength. So these are the tensile and elongation properties. Now, this is the stress strain curve. This yellow line, that is a 0.5% of nanocovalent, is having the highest tensile strength, which is already explained in the table. Now, from FTIR analysis, we found that this curve is almost it is fixed for wool, and it doesn't have much changes since vinyl ester resin that is not chemically binding with the wool, it's only a mechanical binding. Also, the filler, which is the nanocovalent, doesn't have any affinity with the either with the resin or with the wool, so there is no chemical reaction was found. Now, water diffusion properties. When we compared the water diffusion properties of for composite, we found that the control sample, which is having which doesn't have any nanocovalent inside the composite, yielded least water diffusion. And when we are increasing the concentration of nanocovalent, the diffusion also got increased. And this is the DMA analysis, dynamic mechanical analysis. This indicates the viscoelastic properties of wool VR composites. Mainly, we measured the storage modulus, loss modulus, and tan delta. So tan delta, I mean, here also the 0.5% is giving the best result in terms of storage modulus, loss modulus, and tan delta. And TG, TG is highest for control samples. So whenever we are increasing the nanocovalent concentration, it's found that the TG is getting reduced. TG means all of you know that however it is known as glass transition temperature. Now these are the respective curves for loss modulus and tan delta. It's already explained. Now this is the SCM analysis. In SCM analysis, we found that this is the fracture surface of the composites. So we found that we can see different fracture morphologies and different magnification. Especially the debonding is formed in the figure C. Some cracks are visible in figure B. So this indicates that the absence of chemical bond, if the chemical bond is present in between the resin as well as the fiber, this type of gaps or voids may not have formed. So and E indicates the fiber pull out. You can see the fiber is coming out from the composite, and F you can see the nanoparticles. So weight reduction due to biodegradation, as I indicated in previous slides, we have done aging, that is soil burial test, and we found that after soil burial test, that is we kept for 120 days inside the soil for accelerated biodegradation, and still we found only 2.5%, 2.4% is the maximum weight loss due to bacterial degradation. So this is because since wool is biodegradable and this vinyl ester is not biodegradable, obviously ideally it should be higher, but when we are coating the wool fabric with resin, all the wool fiber will be coated, and there is little space for bacteria to come and attack. So that's why the biodegradation is very less. So right side images is showing the wool vinyl ester composite that I prepared in our lab. So this is the accelerated thermal and UV radiation aging. We found that after adding this nanocovalent, the aging properties are getting enhanced in comparison with the control sample. So one of the product, as a product development, we produce one tea coaster from wool vinyl ester composite. This is having 10 centimeter diameter, 35 gram weight, and the ratio to wool and resin is 40:60. So these are my conclusions. We developed a biocomposite with coarse wool with the reinforcement with the vinyl ester resin. Nanocovalent was used to improve the tensile and aging properties. nanocovalent content in the polymer composite was adjusted. That is the optimum strength. It is for 0.5%. With the use of nanocovalent, we found that the aging properties were improved. Regardless of nanocovalent concentration, weight loss due to biodegradation composite were determined as same. So there is no much difference. So one T coaster we developed. I have shown you the images. And finally, what I found that this can be used for also for insulation panels. Also this can be found good application in automobile industries. So thank you very much for giving me an opportunity for my research to present my research findings. Thank you very much.
Okay, thank you very much for the presentation. It was a nice presentation, and now we have time to some questions. So the audience is invited to ask. If not, you can contact by email. And the next presentation, I call upon Farah Amiri, Islamic Azad University of Iran, to deliver her talk on a smart polymeric nanocomposite based on protonated aluminosilicate, curcumin, and chitosan for misaligning drug delivery as an anti-inflammatory nanocarrier. So for Amiri, you are invited to share your screen if you are there. Can you hear me? I don't know. Can you hear me? Are you? Yes, we cannot hear you.
But let me check the.
Now, yes. Maybe you can switch off the video, but to have less. Yes, and just talk and share your screen. If not, it could be overloaded the program and have some issues. Take your time if you can speak a little bit to know if you are there or not.
Can't share my desktop. I don't know why.
I think that the connection. I don't know if you are hear me, but your connection is stopping. You see, intermittent connection. We cannot.
In order to just cover that.
Well, are you there? I think that you can hear me continuously, or your connection to hear me as well, it is stopped.
Obviously, there's no stop between your speaking.
Okay, so it maybe there is a problem with other mode of the connection. So you can talk if you want. Take your time and talk about your subject, your theme, your presentation.
Oh, okay.
You can resume.
I just cannot share my PowerPoint files. Is it okay to continue without that, or you just give me a minute to try for that? I don't know why. I cannot just.
Yes. Take your time. Take a few minutes if you need. If not, I think that maybe if you want to talk as well, you can talk as about your interesting subject and present as best as you can your research. Take your time. We are on time.
Furjan, what is the problem? You can tell me in Farsi if you want.
مرسی من نمیتونم از ویدیو اسکرینمو فعال کنم و قسمتی که شیر اسکرین داره.
شیر اسکرین رو که میزنی قسمت ویندو از یه طرف دیگه پاورپوینت تو باز کن. خب پاورپوینت تو کلا باز کن، بعد همین قسمت توی صفحه زوم شیر اسکرین رو بزن، اون بالا تب ویندو رو بزن، بعد بزن روی آفرین. اوکی. الان دیگه میتونی پاورپوینت الان آره، ولی پاورپوینت تو بذار رو حالت اسلاید شو که بتونی ردش کنی. دیگه نیازی نیست اینور اوکی باشی.
Okay, now we
okay now. Okay. Thank you very much for your
good luck. Okay. Good luck for all.
Thank you. Excuse me for the interruption. My work is about a smart polymeric nanocomposite based on protonate aluminate silicate, curcumin, and ketosol for mesalazine drug delivery as an anti-inflammatory nanocarriers. The titles we are going through is, first of all, inflammatory disease, treatment, methods, and conclusions. Rate for inflammatory bowel disease, or IBD, in the world is about 6.8 million, and high rates are reported in the industrial area. The reason why IBDs occurs is still a mystery, but scientists and researchers believe that some factors such as geographical location, inappropriate diet, gastric genetics, and inappropriate immune condition can be that. Has two main types. The first one is ulcerative colitis that has its own three types: proctitis, terminal colitis, and pancolitis that are shown in the picture. Different types of area of GI that is affected by the IBD. Disease that can affect any part of the GI, and it can be continuous or spotlight. Methods are the treatment of IBD are in two methods. The first one is drug therapy. Anti-inflammatory drugs are often the first step to treat IBD disease for both Crohn's disease or ulcerative colitis. Inflammatory drugs, immune system suppressor, vitamins, painkillers, antibiotics, or antidiarrhea drugs are the drugs that are used during the IBD disease. Surgery. During the surgery, the GI will be removed in order to treat and control the inflammatory. Drugs are for treatment of IBD include corticosteroids and aminosalicylate drugs like mesalamine. Is 5-aminosalicylic acid, or 5-SA, which is used for both ulcerative as a tap or even suppositories. Formula is 3 carbon, 7 hydrogen, and NO3. And material that has been applied through this nanocomposite, or mesoporous, that is the mesoporous form of silica that recently have developed in nanomaterial field. Mesoporous silica nanoparticles, or MSNs, are as carriers for colonic drug delivery has been introduced for their application as a promising platform in medical field in recent decades. And strategy in the field of nanotechnology. The large surface area, high pore size and pore volume, hydrothermal resistance, non-toxicity, safe carriers, considerable biocompatibility and biodegradability, uniform dispersion are the inherent properties of MSN that introduce these nanoparticles, the great candidate as carriers for clonic drug delivery. Something like thing you want to carry with that MSN by that. Best and cost-effective methods for synthesized MSN are soldier that we have applied through this work. Some anti-inflammatory effects. Polyphenol extracted from the rhizome of curcuma luga or turmeric. This material has been used traditionally as a medicine for treatment of a large range of illnesses, such as infectious disease, inflammation. Minimal side effects and abundance of curcumin are the benefits. Existing properties such as sustainability, chemical flexibility, human is the reason of their popularity. The two different form of curcumin, the keto form and the enol form. AMCC synthesized different amount of mesalazine, about 0.1, 0.50, and 0.2 grams of mesalazine have been loaded to the nanocomposite, which we now AMCC, that aluminum, MSN, curcumin, and chitosan. Intermediate nanocomposites and nanomaterials were carried out using several methods, such as FTIR spectroscopy, XRD pattern, SEM images, and nitrogen absorption-desorption isotherms. Those were investigated in vitro spectroscopy of MSN and modified MSN. FTIR spectroscopy of pure MSN, the yellow line upper in the picture, and the three composites of MSN with different characterization of concentration of mesalamine at the range of 400 to 4,000. The functional group among variant AMCC with the different concentration can be identified using FTIR spectroscopy. The non-acidic cyanol groups on the pure MSN surface were observed as a broad band at the range of to 3,600. Represent the wide bonds of at the range of 2,700 to 3,600, attributed to the presence of the carboxylic, phenolic, and amine groups, resulted in the formation of the broad bonds at this area for non-composite samples. At 3430 shows the presence of amine groups AMCC nanocomposite, two bond at the region of 2910 and 2860 are attributed to the CH stretching bond due to the existence of curcumin and chitosan in the nanocomposite structure. The strong peak at 1080 and the medium peak at the 45 attributed to the stretching vibration of the SiO-Si bond. Moreover, the peak of 6030 shows corresponding to the mesalamine as well as chitosan structure in the AMCC nanocomposite in the MSN structure resulted in vibration at around 7 that has been covered by the stretching vibration of SiO-Si bond. Is the next Pattern shows the low angle XRD pattern for the pure MSN, the yellow line. In on a composite with different concentration of mesalamine at a range of 4 to 10 XRD patterns of mesalamine clearly shows the ordered mesoporous silica structure through the presenting of 4 different peaks index 100, 110, and 210 at the low angle degree of 1.5, 5.1, 1.5 to 5.1 index. Illustrated the presence of a 2D hexagonal framework with a spacing around 3.4 nanometers. The load atoms accompanied with a mesalamine molecules into the encapsulated with 2 bulky components of curcumin from 5 degree for MSN to their higher degree of 0.85 degree for all is 4 different peaks were decreased so 200 and 210 approximately, where with which show disordering into the nanocomposite structure. The changed appearance in the peak shows a highest and location of the XRD pattern confirms that the formation of the 3 nanocomposite with irregular silica mesoporous structure. XRD pattern exhibited that the intensity of the highest peak, I mean the 100 peak, more decreased with increasing the mesalamine concentration. Therefore, the crystallinity of the nanocomposite more lead to the less ordered structure with increasing mesalamine species. The next slide is pure MSN and which shows the morphology of the MSN and the nanocomposites. By seeing this image, adding the encapsulating like curcumin or chitosan or even aluminum, the morphology change and the change to kind of disordered. Concentration of mesalamine. This has less grams of mesalazine in this picture. Shows the distinguished difference in the surface area, pore size, and volume of the MSN and modified MSN that observed from 9098 for MSN to 4093 cc with the concentration. And it's due to the occupation of MSN surface area by the various species such as aluminum, chitosan, or curcumin. With the mentioned material resulted in the decrease 26 nanometers for the MSN and AMCC. The result shows that the reduced trend of the surface area, pore size, and size directly is and the loading curcumin or chitosan component, accompanied by mesalamine and aluminum, could affect the reduction of these physical properties. desorption. The chart shows the nitrogen desorption and absorption, isotherm, and pore size distribution of the MSN and AMCC with different, actually. These nanomaterials shows type IV, isotherm H4 of the porous nanomaterials. The isotherm and AMCC nanocomposites infection of the capillary concentration with almost uniform porous structure at a relative pressure of about 0.1 to 0 of the uniform structure. Related pressure of 0.9 to 1 exhibited a slow increase in the absorbed nitrogen that is an evidence to the existence of the weak structure. The moderate nitrogen absorption in the relative pressure at the range of 0.3 to 0.5 structure in the nanocomposite, which describe a narrow pore size distribution at the pore diameter around 1 to 3 nanometers. Of the release process, the mesalamine loading capacity of HAL-MSN nanostructure was investigated. The storage of mesalamine in the modified nanostructure was studied through UV mesalamine solution. In the tunnel was pinking. The reaction between different concentration of mesalamine and HAL-MSN. The color of the solution went light pinkish. One power of HAL-MSN, ish color also. Of mesalamine of the AMCC nanocomposite was under 3 different media pH. The release of mesalamine from the AMCC nanocomposite included different anti-inflammatory drug was investigated in a pH 5.5 and 8. The AMCC nanocomposite was monitored using UV visible spectroscopy in the different acidic, alkaline, and neutral. And at the conclusion, CC nanocomposite were successfully prepared based on protonate aluminum silicate nanoparticles with a high drug loading efficiency in order to drug. Here we use curcumin, anti-inflammatory drug, and also use natural polymer of chitosan for the treatment of colonic disease. Of intermediate and nanomaterials were carried out using several methods, such as FTIR, XRD pattern, SEM images, and nitrogen desorption absorption. Materials were investigated in vitro condition in the different environment, including acid. This evaluation can be led to finding a pathway for mesalamine release in gastrointestinal tissues. It was investigated with accuracy in different pH. That the trend of mesalamine release is higher at the pH of 8. With the efficacy performance more than 90% at room temperature for 19 hours. Thank you, the organization, and all can question or want to contact me, you can use that.
Okay, thank you very much for the presentation. It was a very nice presentation and very interesting. We have 1 minute for a question if there are someone that want to ask her. If not, you can contact her via email or chat. Well, I think that you have there the email. Thank you very much. If you can. Okay. Thank you. The next speaker, I call upon Vladimir Valentinovich Egorov, Russian Academy of Science, Russia, to deliver his talk on quantum classical mechanics, principles, application, and prospect. So, Vladimir, are you there? Can you hear me?
Yes, I hear you, but I must share my presentation.
Yes, take your time.
Just a moment.
Yes, yes, of course. Did you find how to share the screen, or maybe your program is running slowly? Vladimir, are you there? So I don't know if Vladimir can reach us or can hear us. He was there. We are waiting for you. Take your time. Well, if Vladimir cannot, I think that if he's there, okay, you're welcome. We can see your mouse moving. And we are seeing a green slide.
Have you seen my slides?
Yes, now yes.
Yes.
Okay.
Okay. Can I start?
Yes, you can, of course.
Thank you. I'm from Federal Scientific Research Center, Crystallography and Photonics, Russian Academy of Science, Moscow, Russian Federation. My presentation is titled Quantum Classical Mechanics, Principle, Application, and Prospects.
Excuse me, but now we cannot see the slide. Maybe if you put not not open completely, not as presentation.
So you
like
see?
this, yes.
Yes.
Like this, yes. Yes.
Okay. Okay. It is well known that classical mechanics cannot describe, for example, a hydrogen atom. Therefore, more than 100 years ago, the need arose to create a new mechanics, namely quantum mechanics. However, quantum mechanics, like classical mechanics, has a wide but still limited area of its applicability. For example, one of the main branches of quantum mechanics, the theory of quantum transitions, is strictly speaking inapplicable in molecular and chemical physics. Apparently, the first to realize this were Max Born and Robert Oppenheimer, who with their adiabatic approximation proposed to separate the motion of light electrons from the motion of heavy nuclei in a stationary state, thus avoiding consideration of the problem of their joint full-fledged motion. The proposal of the Frank-Condon principle made it possible to avoid considering the problem of joint full-fledged motion of electrons and nuclei also in the process of quantum transition itself. As a result, the whole problem of the dynamics of the quantum electron nuclear or electronic vibrational transition was swept under the carpet like rubbish. Good agreement of this theoretical picture with experimental data on the optical spectra of molecules played a crucial joke here. However, as soon as we pose in theory the question of considering the full-fledged joint motion of electrons and nuclei in the process of transitions, we immediately get a singularity in the transition rates. The presence of this singularity in the dynamics of transitions is associated with incommensurability of the masses of a light electron and heavy nuclei with which it interacts during the transition. This singularity can be easily demonstrated using the example of potential box with a movable wall. Such a wall is, albeit a primitive but a convenient model for understanding transitions in a molecule, in which, along with the electronic transition, the equilibrium positions of oscillating nuclei are shifted, or in other words, the nuclear subsystem is reorganized. The movable ball of the box simulates this reorganization of the nuclei. A standard potential box with a rigid fixed wall is in this case a primitive model of the atom. In order to avoid a singularity in the rate of the transition, we must introduce friction in the base of the wall moving during the transition. A similar procedure should be carried out in exact theory. In the optical version of the new theory, we have as a result a set of the shapes of optical absorption bands with a decrease in friction, which in the exact theory is called transient or dorsey chaos. Such a transformation of the band shape occurs that when k tends to 0, we obtain a singular band shape. The exact theory is considered for the simplest case of the dynamics of elementary dynamics of the relationship between the electron and nuclear motions, namely in the case of elementary electron transfers between the donor and acceptor, which are immersed in the condensed medium. The Hamiltonian of this problem has the form where the first term corresponds to the kinetic energy of the electron, the last term corresponds to the kinetic and potential energy of vibrations of the nuclei of the medium in the harmonic approximation. Q are the normal Fanon coordinates. 1 and 2 are the potential wells of the electron donor and acceptor. This term corresponds to the electron Fanon interaction. Kappa is the Fanon index. E is the energy of reorganization of the medium nuclei associated with the presence of the electron on the donor acceptor. Coded tilde are the shifts of the normal Fanon coordinates associated with this presence of an electron in the medium. As shown in my pioneering works with the framework of standard quantum mechanics, that taking into account of the dynamics of the transient state by the Green's function method, using this Hamiltonian leads to a significant singularity in the rates of quantum transitions. This singularity is eliminated by replacing the infinitesimally small gamma with a finite quantity. This strong singularity, this strong inequality, following from a comparison of theory with experiment, means that the exchange of motion and energy between the electron nuclei in the transient state is so intense that it leads to chaos in the motion of both nuclei and the electron. This transient chaos is called dozy chaos, and in new and no longer quantum mechanics itself is called dozy chaos mechanics. Due to chaos, the energy spectrum of the entire system in a transient state is continuous. In other words, the electron plus nucleus system, which is quantum in the initial and final states, becomes classical in nature in the transient state. Therefore, dozy chaos mechanics can also be called quantum classical mechanics. There is an obvious analogy in the history of the discovery of quantum and the discovery of dozy chaos. The aforementioned replacement of the gamma value in the energy denominator of the Green's function by its finite one, which eliminates the singularity in the rates of molecular quantum transitions, takes physical theory beyond the scope of quantum mechanics and provides us with quantum classical mechanics. This is similar to how the introduction of the finite value of elementary action, the Planck constant, which eliminates the singularity in the spectrum of the absolutely black body, took the physical theory beyond the scope of classical mechanics and gave us subsequently quantum mechanics itself. One of the main results of quantum classical mechanics is a dynamic electron-nuclear organization, or according to a recent article of the journal in the Journal of Physical Chemistry, it is called Egorov resonance, where tau E is the characteristic time of motion of the electron in the donor acceptor system. Tau is the characteristic time of motion of the organization nuclear vibrations in the environment. This time are obtained by the following equations, where L is the distance between the donor and acceptor of the electron, and also L is equal to the length of a polymetallic chain, the main optical chromophore of polymetallic dye. Egorov resonance is an important special case in the dynamics of the transient state of elementary electron transfers in condensed matter. Experimental Egorov resonance manifests itself, for example, in polymetallic dyes, namely in the resonance nature of the dependence of the shape of the optical absorption band on the length of polymetallic chain, as shown in this figure. The optical band with n equals 3 corresponds to Egorov resonance, or is close to it. On the left are experimental data, on the right are the theoretical fitting. This figure demonstrates the efficient performance of quantum classical mechanics in explaining the shape of optical absorption bands for various aggregates of polymetallic dyes. One of these aggregates are the well-known J aggregates that have a narrow and intense absorption band and are widely used in practice. According to the standard theory, which ignores the dynamics of the transient state, the transition from absorption spectrum to luminescence spectra is carried out by changing the sign before the heat energy delta. On the right are the shapes of the optical absorption bands dependent on the dose case energy gamma, which are shown in the slide 2. On the left, the same band shapes are given after a sign change in the heat energy delta, that is for luminescence. This slide shows a comparison of variable experiment. It can be seen then that when the sign changes only in the value of delta, the theoretical absorption luminescence spectra turn out to be symmetric with respect to each other. While experiment shows the asymmetry, this absorption, this luminescence. According to quantum classical mechanics, which takes into account the dynamics of the transient state, in addition to changing the sign of in the heat energy delta, and it is also necessary to change the sign before the length of the optical chromophore L, or equivalently before the electron charge transfer distance L. After that, as we see, the theory reproduces well the asymmetry of the absorption and luminescence spectra, which is observed in the experiment. Next, I will say a few words about the problem to be solved within the framework of quantum classical mechanics, or with its help in the near and distant future. The primary task is to generalize quantum classical mechanics to the case of nonlinear optics. This slide shows the experimental shapes of optical bands for 1 photon and 2 photon absorption of some polymetallic dye in a solvent chloroform. In the case of a single photon absorption, the band is rather narrow and intense, and therefore it can be assumed that it corresponds to Igorov resonance. When going to 2 photon absorption, the shape of the band sharply deteriorates, which is associated with a strong violation of condition of this resonance. In this slide, both of these experimental band shapes are simulated with the framework of what we have so far, quantum classical mechanics in the case of a 1 photon absorption. This slide showed the same 2 band shapes, but for photon energy on the abscissa axis. Under resonance conditions with 1 photon absorption, it can be said that the single acts of absorption of photon and energy occurs most likely in the region of the band peak, and with the less probability in the region of its wing. In the transition from resonant 1 photon absorption to 2 photon absorption, a substantial shift of the main photon absorption region, namely from the low energy peak of the band to high energy wing, occurs. To return the system polymetallic dye plus environment to Igorov resonance, but already under conditions of 2 photon absorption, it is necessary to reduce either the solvent reorganization energy or the polymetallic chain length in the experimental conditions. This slide illustrates the conditions for the for restoration of the ego of resonance by studying the dependence of the shape of the model two-photon absorption band on the reorganization energy. It is predicted that the resonance under conditions of a two-photon experiment shifts to the red region, and it should be thought using a non-polar solvent somewhere on the border of the red and infrared region. For an accurate clarification of the conditions for the restoration of the Igor resonance, it is necessary to construct quantum classical mechanics for the case of nonlinear optics, which was mentioned above. From the point of view of theoretical physics, it is of interest to solve the inverse problem by the form of the complete green function of the system, in which infinitesimal imagery additive I gamma in the energy denominator is replaced by a finite value, to find the form of the original non-Hamiltonian that corresponds to such a modified green function. Quantum classical mechanics can be considered as a kind of a generalization of quantum mechanics in which a new property of the electron is revealed. This new property consists in the ability to provoke chaos in the vibrational motion of nuclei in the process of molecular quantum transitions. The ability of the electron to create those chaos is a prerequisite for the implementation of molecular quantum transitions, elementary electron transfers in condensed matter, and their more general form, elementary chemical reactions. Therefore, the electron ability shows us the physical source of the complication and self-organization of molecular matter, up to the emergence of living matter and man and self, which are the results of the targeted dynamic activity when astronomically large number of light electrons in nature subordinated to their will and equally astronomically large number of very heavy nuclei. The ultimate goal of such electron activity is to create the human brain and associated human consciousness in the evolution, and the living brain is the part of the body in which those chaos is concentrated to the greatest extent. When we fall asleep, the dose chaos radiation largely moves from the brain to other parts of the body, and when we wake up, it returns to the brain. It is such a periodic motion of weak dose chaos radiation, which is an electromagnetic nature throughout the body during the day and night, from the brain and back, provides an effective rest and work of the brain. This is the physical nature of sleep. In this context, the problem of cancer and problem of viral infections acquire their theoretical foundations in quantum classical mechanics. Here the list of my publications. Thank you. In this appendix, I reproduce the theoretical equations which on the basis of which are calculated the band shapes shown above. Thank you very much.
Okay, thank you very much, Vladimir. It was a very nice presentation, very interesting, with high impact insights from the quantum to the biology. I think that maybe there are some questions from the audience. If not, you can contact him via email or chat later. So thank you very much, Vladimir. If you can stop to share your screen.
Thank you.
Thank you too. Well, the next speaker I call upon Mohamed Shasir, California Institute of Behavioral Neuroscience and Psychology from United States. The presentation will be focused on application of nanotechnology for diagnosis and drug delivery in arteriosclerosis, a new horizon of treatment. So if Mohamed is there, you are welcome to share your screen and talk.
Thank you for the wonderful introduction, Guillermo. And good evening,
You're welcome.
everyone. Nice to be here. Thank you for having me as a part of your team. So we'll be discussing the application of nanotechnology for the diagnosis as well as the drug delivery in atherosclerosis. Can you guys see my screen? Is it visible?
Yes, we can. Maybe you can zoom out. Sometimes the presentation mode, it could be stopped, but like that, I think that we can see.
Oh, okay. So cardiovascular diseases, I'm just going to give a little bit of introduction before we begin and delve into nanotechnology. Cardiovascular diseases are the leading causes of death worldwide. It just more than 17 million people just in 2019, where COVID was at the peak. So this accounts for just above 30% of all global deaths. And the way we diagnose atherosclerosis nowadays is we use imaging. And imaging is not always 100% reliable. And that's why we came up with the idea of introducing nanotechnology into already existing imaging techniques, as well as other drugs into in how we can approach this problem in diagnosing as well as treating atherosclerosis before it gets your heart, it clenches your heart. So that is why we recommend nanotechnology as a novel drug delivery method. So the primary objective in the clinical setting is introduction of nanotechnology and nanoparticles to deliver poorly water-soluble drugs in a specific manner, whether it is cell or tissue specific. And then it transcytos the drug across both the epithelial and endothelial barriers, thereby facilitating the delivery of not one or two, maybe more than the required number of drugs. And we have seen a significant reduction in the circulation of plasma lipids, especially the bad cholesterol, as we call it, the LDL cholesterol. So it has been reported in several studies across the globe, and it has been reproduced several times. So we evaluated the outcome with standard diagnostic procedures like magnetic resonance imaging and fluorescence imaging. So one might ask, why all the fuss about nanotechnology and nanoparticles, especially in atherosclerosis? That's because we've had several problems. Without nanoparticles, we wouldn't be able to bring the system, bring the particles into the drug stream. And even if we did, it would degrade within a couple of minutes. So, and there is also this problem of photo bleaching and the rapid disintegration. So utilizing nanotechnology has immensely helped us in providing a solution. So we have several fluorescence imaging techniques, like one of the dyes we use is CY 5.5. So when we couple this with nanoparticles, we can solve the problem of rapid biodegradation, and we can also use it in imaging. And also there is this novel S100A9 targeted tobacco mosaic virus nanoparticles. And this S100A9 is a specific protein found in atherosclerotic lesions prone to rupture. So in atherosclerosis is where there are plaque burdens in your major blood vessels, especially the ones supplying the heart. So as long as it doesn't rupture, you wouldn't cause any problems. But once it ruptures, we call this entirety myocardial infarction. So our goal is to primarily prevent myocardial infarction and maybe even the progression of atherosclerosis with the introduction of nanoparticles. So moving on, if you would focus on the last column, I have highlighted the nanoparticles that we have studied, especially in the therapeutic application in atherosclerosis. So the first one would be squalene and squalene rhodoamine nanoparticles, and this was primarily in vivo. They studied this in rodents iotas, and they found that this was able to identify the presence of atherosclerotic lesions in the rodents. Next one would be the tobacco mosaic virus nanoparticles. And then again, ApoE deficient mice is ApoE is a gene that is very closely related with atherosclerosis. And if you if you don't have ApoE, there is a very high chance that you might get atherosclerosis in your early 20s as well as 30s, and soon might get myocardial infarction. So they targeted ApoE deficient mice, and once they clubbed the tobacco mosaic virus nanoparticles, they were especially very prone to these atherosclerotic lesions. The next would be PLGA nanoparticles, polylactic glycolic acid nanoparticles, and injection of nanoparticles has proven to decrease this PLGA nanoparticles has proven to decrease more than 64% of the LDL cholesterol, which is responsible for the major pathophysiology of atherosclerosis. Then we have the SIM PMBP nano composite, which is the porous manganese substitute Prussian blue nano composite. So what it did, this study was aimed at studying learning how the pathophysiology of atherosclerosis is closely concerned with nanoparticles. So they were Zhang et al. In 2021 was able to observe oxidative stress, how it reduces oxidative stress, the plaque density, and even the LDL internalization, as well as the reduction in macrophages, because macrophages play a huge role when it comes to atherosclerosis and the angiogenesis and inflammatory properties. So once we get rid of all these things and fibrous cap thickness, it can lead to a rapid reduction in the rate of atherosclerotic progression, and even their rupture, which sometimes might be fatal. We won't have a lot of time to save these patients. It might be a couple of seconds, and the next thing you know, the patient goes into cardiac arrest. Not only this, this triple P, that is the polylactic glycolic acid, polyethylene glycol, and polylactic glycolic acid nanoparticles, we were able to observe about half decrease in the lesion of the stenotic lesions, decrease in almost half the size of the plaque. So this was primarily due to the droplet vaporization, and which facilitates apoptosis of raw macrophages. Apoptosis is a cell death of raw macrophages. So that means the progression of atherosclerosis has literally stopped. Then we have the raspberry linked platinum and the serum bimetallic nanostructure. The study by SU et W et al. In 2022. This is a very recent study, by the way. They observed a significant control of atherosclerotic area in high-fat diet-fed ApoE deficient mice. Again, ApoE is a gene without which there is a lot of risk for atherosclerosis, especially the plaque rupture as well as the plaque burden. In this scenario, there were a lot of reduction in the atherosclerotic area. So more than 70% of the area, if it was supposed to have more than 70% of the area, you might call this clinical entity angina, which means you won't be able to perform your routine activities of physical living, like maybe walking to the gym or taking a stroll down the road. So this was raspberry linked platinum and cerium bimetallic nanostructure proved to be fruitful when it came to treating atherosclerotic lesions. And then comes the zinc dioxide and catalyst co-loaded porous PLGA. Again, most of the studies that I've mentioned are in vivo studies. There were also in vitro studies, but I chose to focus my presentation on in vivo studies. So all of these studies, they efficiently reduce the plaque burden as well as reduction in the atherosclerotic area. Some were able to reduce more than half the plaque burden, some 65, 70%, some 30 or 40%. Nevertheless, all of these nanoparticles proved to be tremendously helpful in reducing the atherosclerotic plaque. And this is also a recent study as well, a molecularly imprinted Syria nanocomposite CEO2 nanoparticle. Again, this was studied in ApoE deficient mice. ApoE deficient mice is the ideal lab rat for atherosclerosis. So lipid lowering abilities were demonstrated, similar to the ones that we find in statins. Any cardiovascular patient would be put on a statin to make sure they don't get a heart attack or the progression of the atherosclerosis. So we'll be discussing the therapeutic applications first. Just like we've mentioned before, there are various studies. The one by Brusini or Deshpande, they've all demonstrated the beneficial effects of squalene conjugates, natural lipids, endogenous immunomodulator, and encapsulation with alpha tocopherol. Alpha tocopherol is vitamin E. So it's an antioxidant that resulted in the formulation of a nanoparticle. It's incredibly hard to find a particle that is biocompatible. If it's not biocompatible, there is no use studying it in the lab or even in animals. So this is where nanotechnology comes in action. And also Deshpande and et al. They demonstrate the beneficial effect of CRECA. CRECA is a linear polypeptide, and it's a compound of 5 amino acids. So this nanoemulsion against atherosclerosis with multifunctional benefits by 1, reduction of the lesion size, 2, the lowering of the circulating plasma lipids, especially the LDL cholesterol, which is the culprit in most of atherosclerotic lesions, and 3, decreasing the gene expression of inflammatory markers like interleukin 1, interleukin 6, tumor necrosis factor alpha. These are various inflammatory markers that go on to erode our blood vessels. So CRECA peptide modified nanoemulsion has been proven. Again, imatinib nanoparticles were also found to be especially especially helpful when treating the saphenous venous graft. How do we call it? The bypass, the coronary artery bypass graft, the one where we take the saphenous vein from the venous veins from the legs, and we bypass the blocked arteries. Usually, we do it when we have major arterial occlusion in all the 3 arteries. There are 3 major arteries supplying the heart, and when all of these 3 are thriving for blood, what they do is they take a graft and then they bypass the system. So sometimes what happens is, even after you perform a bypass surgery, you might have heard 1 or 2 people are getting heart attacks again. Why does this happen? That's because atherosclerosis again happens in the venous graft, or maybe the graft wasn't successful. So in order to tackle this, we have this imaginative nanoparticles. Uh, as I've told you, some nanoparticles were reduce the plaque reduction by more than 50%. So in this scenario, Zhang et al., they noted a twofold increase in the hallmark of atherosclerotic sim-loaded theranostic agents. LDL internalization, macrophage. We are talking at the subcellular level, macrophage infiltration in fibrous cap thickness, and foam cell birth. Foam cells are basically the hallmarks of atherosclerotic lesions. The impact of nanotechnology and LDL internalization, this was also backed up by Koga et al. This is also a very recent study. So a significant reduction in the levels of circulating plasma lipids were also noted, in addition to a decline in the gene expression of hallmark inflammatory markers of atherosclerosis. Even in diagnosis, we might get to see nanoparticles playing a huge role in the next 5, if not 10 years. So one study by Key et al. In 2021 recorded that it was an excellent tool for the diagnosis of atherosclerosis, especially in the early stages. It's incredibly hard to diagnose atherosclerosis. Actually, atherosclerosis starts very early, as I told you earlier, and it's incredibly hard to diagnose it early. So, with the implication of nanoparticles in the diagnostic application of atherosclerosis should make way for future clinical trials, especially in human beings. The results reported that STP VCAM CUR CY 5.5. This CY 5.5 is a fluorescent dye that's used in fluorescence imaging of atherosclerosis. So it's used for magnetic resonance and fluorescent imaging, and for delivering chemotherapeutic agents to the inflammatory tissues. Lee et al. Utilized class A1 scavenger receptors targeted glutathione biomineralized gadolinium-based nanoparticles. Gadolinium is usually one of the contrast things we use in magnetic resonance imaging for the macrophages present within the patient's atherosclerotic lesions of the carotid arteries. So the findings of this study in vivo demonstrated augmented MRI signaling. So what this does is we might be able to diagnose atherosclerosis way before it manifests itself, and maybe personalized. This is called personalized medicine. Maybe we can reduce the atherosclerotic risk factors. Some of them which are really modifiable, like smoking, diet, sedentary lifestyle. CHANs, which are cross-linked hyaluronic acid nanoparticles decorated with the anti-3D CD36 antibody, has also demonstrated the atherosclerotic plaque-associated macrophage targeting. We've talked about S100A9, that a protein found in atherosclerotic lesions prone to rupture. So once we get a hold of S100A9 with application of nanotechnology, we might just be able to identify the culprit lesion in atherosclerosis. So all nanoparticles that we've studied, we studied 14. We've collected information from 14 different articles in the last 60, 70 years or so. And we use systematic review based on Prisma guidelines. And all of the nanoparticles that we studied noted a superior, if not a non-inferior, therapeutic and diagnostic benefit to current approaches in diagnosis as well as treating atherosclerosis. So we might be able to compare and contrast these nanoparticles, and if we are successful, multifunctional nanoparticles, we might be able to deliver more than one nanoparticle. Like you might have heard of statins. There is a drug called pitavastatin. Currently, there is a research, and this research aims to deliver a pitavastatin inside the blood vessels with the aid of nanotechnology. So if that were to happen, we might see a drastic reduction in atherosclerotic plaque burden, and this just might reduce the burden of cardiovascular diseases worldwide. So this is our article. I was the second author, and if you'd like to have a look at it, I've put it in put up the DOI as my first reference. So please feel free to ask any questions, and thank you for having me.
Okay, thank you very much, Mohammed, for your presentation. It was very nice and interesting with real high impact in our lives, life science. So if there are some questions, you can ask him now or send him an email or chat with him. Well, if there are not questions, the organizing committee
Yes.
will close.
Yeah, thank you, Dr. Guillermo. Thanks for your support. Myself, Victor, on behalf of Scholars Conferences, I would like to thank you all the participants for making this event a great success. I especially thanks Dr. Guillermo, the moderator of the day. I expect all of you to have had a great time. We'll be glad to hear your feedback. It would be great if you could share your feedback as a testimony or email to the conference organizer, and all your certificates will be sent to you via email. All the participant certificates will be sent, and hope everyone will join us at the 24 event, which is in the month of March in Valencia, Spain, 2024. Thank you. Hope you had a great day. See you in 2024 Nanotech. Thank you.
Thank you very much as well.